Welcome to this course on the practical aspects of deep learning. Perhaps now you've learned how to implement a neural network. In this week, you'll learn the practical aspects of how to make your neural network work well, ranging from things like hyperparameter tuning, to how to set up your data, to how to make sure your optimization algorithm runs quickly so that you get your learning algorithm to learn in a reasonable amount of time. In this first week, we'll first talk about how to set your machine learning problem, then we'll talk about regularization, and we'll talk about some tricks for making sure your neural network implementation is correct. With that, let's get started. Making good choices in how you set up your training, development, and test sets can make a huge difference in helping you quickly find a good, high-performance neural network. When training a neural network, you have to make a lot of decisions, such as how many layers will your neural network have, and how many hidden units do you want each layer to have, and what's the learning rate, and what are the activation functions you want to use for the different layers. When you're starting out on a new application, it's almost impossible to correctly guess the right values for all of these and for other hyperparameter choices on your first attempt. So in practice, applied machine learning is a highly iterative process in which you often start with an idea, such as you want to build a neural network of a certain number of layers, a certain number of hidden units, maybe on certain data sets and so on. And then you just have to code it up and try it. By running your code, you run and experiment and you get back a result that tells you how well this particular network or this particular configuration works. And based on the outcome of, you might then refine your ideas and change your choices and maybe keep iterating in order to try to find a better and a better neural network. Today, deep learning has found great success in a lot of areas, ranging from natural language processing to computer vision to speech recognition, to a lot of applications on also structured data. And structured data includes everything from advertisement to web search, which isn't just internet search engines, it's also, for example, shopping websites, or really any website that wants to deliver great search results when you enter terms into a search bar, to computer security, to logistics, such as figuring out where to send drivers to pick up and drop off things, to many more. So what I've seen is that sometimes a researcher with a lot of experience in NLP might might try to do something in computer vision, or maybe a researcher with a lot of experience in speech recognition might jump in and try to do something on advertising, or someone from security might want to jump and do something on logistics. And what I've seen is that intuitions from one domain or from one application area often do not transfer to other application areas. And the best choices may depend on the amount of data you have, the number of input features you have, your computer configuration, and whether you're training on GPUs or CPUs, and if so, exactly what configuration of GPUs and CPUs, and many other things. So for a lot of applications, I think it's almost impossible. Even very experienced deep learning people find it almost impossible to correctly guess the best choice of hyperparameters the very first time. And so today, applied deep learning is a very iterative process where you just have to go around this cycle many times to hopefully find a good choice of network for your application. So one of the things that'll determine how quickly you can make progress is how efficiently you can go around this cycle. And setting up your data sets well in terms of your train, development, and test sets can make you much more efficient at that. So if this is your training data, let's draw that as a big box, then traditionally you might take all the data you have and carve off some portion of it to be your training set, some portion of it to be your holdout cross-validation set, and this is sometimes also called the development set. And for brevity, I'm just going to call this the dev set, but all of these terms mean roughly the same thing. And then you might carve out some final portion of it to be your test set. And so the workflow is that you keep on training algorithms on your training set and use your dev set or your holdout cross-validation set to see which of many different models performs best on your dev set. And then after having done this long enough, when you have a final model that you want to evaluate, you can take the best model you found and evaluate it on your test set in order to get a unbiased estimate of how well your algorithm is doing. So in the previous era of machine learning, it was common practice to take all your data and split it according to maybe a 70-30%. In terms of people often talked about the 70-30 train test split if you don't have an explicit dev set, or maybe a 60-20-20% split in terms of 60% train, 20% dev, and 20% test. And several years ago, this was widely considered best practice in machine learning. If you have, maybe 100 examples in total, maybe 1,000 examples in total, maybe up to 10,000 examples, these sorts of ratios were perfectly reasonable rules of thumb. But in the modern big data era, where, for example, you might have 1 million examples in total, then the trend is that your dev and test sets have been becoming a much smaller percentage of the total. Because remember, the goal of the dev set, the development set, is that you're going to test different algorithms on it and see which algorithm works better. So the dev set just needs to be big enough for you to evaluate, say, 2 different algorithm choices or 10 different algorithm choices and quickly decide which one is doing better. And you might not need a whole 20% of your data for that. So for example, if you have 1 million training examples, you might decide that just having 10,000 examples in your dev set is more than enough to evaluate, which one of 2 algorithms does better. And in a similar vein, the main goal of your test set is, given your final classifier, to give you a pretty confident estimate of how well it's doing. And again, if you have 1 million examples, maybe you might decide that 10,000 examples is more than enough in order to evaluate a single classifier and give you a good estimate of how well it's doing. So in this example, where you have 1 million examples, if you need just 10,000 for your dev and 10,000 for your test, your ratio would be more like this 10,000 is 1% of 1 million. So you'd have 98% train, 1% dev, 1% test. And I've also seen applications where if you have even more than 1 million examples, you might end up with 99.5% train and 0.25% dev, 0.25% test, or maybe a 0.4% dev, 0.1% test. So just to recap, when setting up your machine learning problem, I'll often set it up into a train, dev, and test sets. And if you have a relatively small data set, these traditional ratios might be okay. But if you have a much larger data set, it's also fine to set your dev and test sets to be much smaller than 20% or even 10% of your data. We'll give more specific guidelines on the sizes of dev and test sets later in this specialization. One other trend we're seeing in the era of modern deep learning is that more and more people train on mismatched train and test distributions. Let's say you're building an app that lets users upload a lot of pictures, and your goal is to find pictures of cats in order to show your users. Maybe all your users are cat lovers. Maybe your training set comes from cat pictures downloaded off the internet, but your dev and test sets might comprise cat pictures from users using our app. So maybe your training set has a lot of pictures crawled off the internet, but the dev and test sets are pictures uploaded by users. Turns out a lot of web pages have very high resolution, very professional, very nicely framed pictures of cats, but maybe your users are uploading, blurrier, lower res images just taken with a cell phone camera in a more casual condition. And so these two distributions of data may be different. The rule of thumb I'd encourage you to follow in this case is to make sure that the dev and test sets come from the same distribution. We'll say more about this particular guideline as well, but because you will be using the dev set to evaluate a lot of different models and trying really hard to improve performance on the dev set, it's nice if your dev set comes from the same distribution as your test set. But because deep learning algorithms have such a huge hunger for training data, One trend I'm seeing is that you might use all sorts of creative tactics, such as crawling web pages, in order to acquire a much bigger training set than you would otherwise have, even if part of the cost of that is then that your training set data might not come from the same distribution as your dev and test set. But you find that so long as you follow this rule of thumb, that progress in your machine learning algorithm will be faster. And I'll give a more detailed explanation for this particular rule of thumb later in the specialization as well. Finally, it might be okay to not have a test set. Remember, the goal of the test set is to give you a unbiased estimate of the performance of your final network, of the network that you selected. But if you don't need that unbiased estimate, then it might be okay to not have a test set. So what you do, if you have only a dev set but not a test set, is you train on the training set, and then you try different model architectures, evaluate them on the dev set, and then use that to iterate and try to get to a good model. Because you fit your data to the dev set, this no longer gives you an unbiased estimate of performance, but if you don't need one, that might be perfectly fine. In the machine learning world, when you have just a train and a dev set, but no separate test set, most people will call this the training set, and they will call the dev set the test set. But what they actually end up doing is using the test set as a holdout cross-validation set, which maybe isn't completely a great use of terminology because they're then overfitting to the test set. So when a team tells you that they have only a train and a test set, I would just be cautious and think, do they really have a train dev set because they're overfitting to the test set? Culturally, it might be difficult to change some of these teams' terminology and get them to call it a train dev set rather than a train test set. Even though I think calling it a train and development set would be more correct terminology. And this is actually okay practice if you don't need a completely unbiased estimate of the performance of your algorithm. So having set up a train, dev, and test sets will allow you to iterate more quickly. It will also allow you to more efficiently measure the bias and variance of your algorithm so that you can more efficiently select ways to improve your algorithm. Let's start to talk about that in the next video. I've noticed that almost all the really good machine learning practitioners tend to have a very sophisticated understanding of bias and variance. Bias and variance is one of those concepts that's easy to learn but difficult to master. Even if you think you've seen the basic concepts of bias and variance, there's often more nuance to it than you'd expect. In the deep learning era, another trend is that there's been less discussion of what's called the bias-variance trade-off. You might have heard of this thing called the bias-variance trade-off. But in the deep learning era, there's less of a trade-off. So we still talk about bias, we still talk about variance, but we just talk less about the bias-variance trade-off. Let's see what this means. Let's say you have a data set that looks like this. If you fit a straight line to the data, maybe you get a logistic regression fit to that. This is not a very good fit to the data, and so there's a class of high bias, or we say that this is underfitting the data. On the opposite end, if you fit an incredibly complex classifier, maybe a deep neural network or a neural network with a lot of hidden units, maybe you can fit the data perfectly, but that doesn't look like a great fit either. So this is a classifier with high variance, and this is overfitting the data. And there might be some classifier in between with a medium level of complexity that, maybe fits a curve like that. That looks like a much more reasonable fit to the data. And so that's maybe we call that, just right, somewhere in between. So in a 2D example like this, with just two features, x1 and x2, you can plot the data and visualize bias and variance. In high-dimensional problems, you can't plot the data and visualize the decision boundary. Instead, there are a couple different metrics that we'll look at to try to understand bias and variance. So continuing our example of cat picture classification, where that's a positive example and that's a negative example, the two key numbers to look at to understand bias and variance will be the training set error and the dev set or the development set error. So for the sake of argument, let's say that recognizing cats in pictures is something that people can do nearly perfectly, right? And so let's say your training set error is 1%, and your dev set error is, for the sake of argument, let's say is 11%. So in this example, you're doing very well on the training set, but you're doing relatively poorly on the development set. So this looks like you might have overfit the training set. that somehow you're not generalizing well to this whole cross-validation set or the development set. And so if you have an example like this, we would say this has high variance. So by looking at the training set error and the development set error, you would be able to render a diagnosis of your algorithm having high variance. Now, let's say that you measure your training set and your depth set error, and you get a different result. Let's say that your training set error is 15%. I'm writing your training set error in the top row, and your depth set error is 16%. In this case, assuming that humans achieve, roughly 0% error, that humans can look at these pictures and just tell if it's a cat or not, then it looks like the algorithm is not even doing very well on the training set. So if it's not even fitting the training data as seen that well, then this is underfitting the data, and so this algorithm has high bias. But in contrast, it's actually generalizing at a reasonable level to the depth set, whereas performance of the depth set is only 1% worse than its performance on the training set. So this algorithm has a problem of high bias because it's not even fitting the training set well. This is similar to the leftmost plot we had on the previous slide. Now, here's another example. Let's say that you have 15% training set error, so that's pretty high bias. But when you evaluate on a depth set, it does even worse. Maybe it does 30%. In this case, I would diagnose this algorithm as having high bias because it's not doing that well on the training set, and high variance. So this is really the worst of both worlds. And one last example, if you have 0.5 training set error and 1% depth set error, then maybe your users are quite happy that you have a CAT classifier with only 1% error. Then this would have low bias and low variance. One subtlety that I'll just briefly mention, but will leave to a later video to discuss in detail, is that this analysis is predicated on the assumption that human-level performance gets nearly 0% error, or more generally, that the optimal error, sometimes called Bayes error, for the Bayesian optimal error, is nearly 0%. I don't want to go into detail on this in this particular video, but it turns out that if the optimal error or the Bayes error were much higher, say it were 15%, then if you look at this classifier, 15% is actually perfectly reasonable for a training set, and you wouldn't say that's high bias, and it will also have pretty low variance. So the case of how to analyze bias and variance when no classifier can do very well. For example, if you have really blurry images so that even a human or just no system could possibly do very well, then maybe Bayes error is much higher, and then there's some details to how this analysis would change. But leaving aside this subtlety for now, the takeaway is that by looking at your training set error, you can get a sense of how well you're fitting at least the training data, and so that tells you if you have a bias problem. And then looking at how much higher your error goes when you go from the training set to the depth set, that should give you a sense of how bad is the variance problem. So are you doing a good job generalizing from the training set to the depth set? That gives you a sense of your variance. All this is under the assumption that the Bayes error is quite small and that your train and your depth sets are drawn from the same distribution. If those assumptions are violated, there's a more sophisticated analysis you could do, which we'll talk about in the later video. Now, on the previous slide, you saw what high bias, high variance looks like, and I guess you had a sense of what a good classifier looks like. What does high bias and high variance looks like? It's kind of the worst of both worlds. So you remember we said that a classifier like this, a linear classifier, has high bias because it underfits the data. So this would be a classifier that is mostly linear and therefore underfits the data. We're drawing this in purple. But if somehow your classifier does some weird things, then it's actually overfitting parts of the data as well. So the classifier that I drew in purple has both high bias and high variance. Right, that's high bias because by being a mostly linear classifier, it's just not fitting, this quadratic light shape that well. But by having too much flexibility in the middle, it somehow gets this example and this example overfits those two examples as well. So this classifier kind of has high bias because it was mostly linear, but you needed maybe a curve function, a quadratic function, and it has high variance because it had too much flexibility to fit those two mislabeled or those outlier examples in the middle as well. In case this seems contrived, well, this example is a little bit contrived in 2 dimensions, but with very high dimensional inputs, you actually do get things with high bias in some regions and high variance in some regions. And so it is possible to get classifiers like this in high dimensional inputs that seem less contrived. So to summarize, you've seen how by looking at your algorithm's error on the training set and your algorithm's error on the depth set, you can try to diagnose whether it has a problem of high bias or high variance, or maybe both, or maybe neither. And depending on whether your algorithm suffers from bias or variance, it turns out that there are different things you could try. So in the next video, I want to present to you what I call a basic recipe for machine learning that lets you more systematically try to improve your algorithm depending on whether it has high bias or high variance issues. So let's go on to the next video. In a previous video, you saw how looking at training error and depth error can help you diagnose whether your algorithm has a bias or a variance problem, or maybe both. It turns out that this information that lets you much more systematically, using what I call a basic recipe for machine learning, it lets you much more systematically go about improving your algorithm's performance. Let's take a look. When training a neural network, here's a basic recipe I would use. After having trained an initial model, I would first ask, does your algorithm have high bias? And so to try to evaluate if there's high bias, you should look at really the training set or the training data performance, right? And so if it does have high bias, so it's not even fitting the training set that well, some things you could try would be to try a bigger network, such as more hit layers or more hidden units, or you could train it longer, maybe run gradient and longer, or try some more advanced optimization algorithms, which we'll talk about later in this course. Or you could also try, this is kind of maybe it'll work, maybe it won't, but we'll see later that there are a lot of different neural network architectures, and maybe you can find a neural network architecture that's better suited for this problem. Putting this in parentheses, because one of those things that, you just have to try, maybe you can make it work, maybe not, whereas getting a bigger network almost always helps, and training longer, well, doesn't always help, but it certainly never hurts. But so when training a learning algorithm, I would try these things until I can at least get rid of the bias problems. As if go back after I've tried this until, and keep doing that until I can at least fit the training set pretty well. And usually, if you have a big enough network, you should usually be able to fit the training data well, so long as there's a problem that is possible for someone to do, right? If an image is very blurry, it may be impossible to fit it, but if at least a human can do well on the task, if you think Bayes' error is not too high, then by training a big enough network, you should be able to hopefully do well, at least on the training set, to at least fit or overfit the training set. Once you've reduced bias to a acceptable amounts, I would then ask, do you have a variance problem? And so to evaluate that, I would look at the depth set performance. Right? Are you able to generalize from a pretty good training set performance to having a pretty good depth set performance? And if you have high variance, well, best way to solve a high variance problem is to get more data. If you can get it, this can only help, but sometimes you can't get more data. Or you could try regularization, which we'll talk about in the next video, to try to reduce overfitting. And then also, again, this is sometimes you just have to try it. But if you can find a more appropriate neural network architecture, sometimes that can reduce your variance problem as well as reduce your bias problem. But how to do that? It's harder to be totally systematic in how you do that. But so I try these things and kind of keep going back until hopefully you find something with both low bias and low variance, whereupon you would be done. So a couple points to notice. First is that depending on whether you have high bias or high variance, the set of things you should try could be quite different. So I'll usually use the train and depth set to try to diagnose if you have a bias or variance problem, and then use that to select the appropriate subset of things to try. So for example, if you actually have a high bias problem, getting more training data is actually not going to help, or at least it's not the most efficient thing to do. Right? So being clear on how much of a bias problem or variance problem or both can help you focus on selecting the most useful things to try. Second, in the earlier era of machine learning, there used to be a lot of discussion on what's called the bias-variance trade-off. And the reason for that was that for a lot of the things you could try, you could increase bias and reduce variance, or reduce bias and increase variance. But back in the pre-deep learning era, we didn't have many tools. We didn't have as many tools that just reduce bias or that just reduce variance without hurting the other one. But in the modern deep learning big data era, so long as you can keep training a bigger network and so long as you can keep getting more data, which isn't always the case for either of these, but if that's the case, then getting a bigger network almost always just reduces your bias without necessarily hurting your variance, so long as you regularize appropriately. And getting more data pretty much always reduces your variance and doesn't hurt your bias much. So what's really happened is that with these two steps, the ability to train a bigger network or get more data, we now have tools to drive down bias, and just drive down bias, or drive down variance and just drive down variance without really hurting the other thing that much. And I think this has been one of the big reasons that deep learning has been so useful for supervised learning, that there's much less of this trade-off where you have to carefully balance bias and variance, but sometimes you just have more options for reducing bias and reducing variance without necessarily increasing the other one. And in fact, so long as you have a well-regularized network, we'll talk about regularization starting from the next video, training a bigger network almost never hurts. And the main cost to training a neural network that's too big is just computational time, so long as you're regularizing. So I hope this gives you a sense of the basic structure of how to organize your machine learning problem to diagnose bias and variance and then try to select the right operation for you to make progress on your problem. One of the things I mentioned several times in the video is regularization. It's a very useful technique for reducing variance. There is a little bit of a bias-variance trade-off when you use regularization. It might increase the bias a little bit, although often not too much if you have a huge enough network. But let's dive into more details in the next video so we can better understand how to apply regularization to your neural network. If you suspect your neural network is overfitting your data, that is, if you have a high variance problem, one of the first things you should try is probably regularization. The other way to address high variance is to get more training data. That's also quite reliable, but you can't always get more training data. It could be expensive to get more data, but adding regularization will often help to prevent overfitting or to reduce variance in your neural network. So let's see how regularization works. Let's develop these ideas using logistic regression. Recall that for logistic regression, you try to minimize the cost function j, which is defined as this cost function, sum over your training examples of the losses of the individual predictions and the different examples, where you recall that w and b in logistic regression are the parameters. So w is an x-dimensional parameter vector and b is a real number. And so to add regularization to logistic regression, what you do is add to it this thing, lambda, which is called the regularization parameter. I'll say more about that in a second, but lambda over 2m times the norm of w squared. So here, the norm of w squared is just equal to sum from j equals 1 to nx of wj squared, or this can also be written w transpose w is just a square Euclidean norm of the parameter vector w. And this is called L2 regularization, because here you're using the Euclidean norm, also called the L2 norm of the parameter vector w. Now, why do we regularize just the parameter w? Why don't we add something here, about b as well? In practice, you could do this, but I usually just omit this, because if you look at your parameters, w is usually a pretty high-dimensional parameter vector, especially with a high variance problem. Maybe w just has a lot of parameters, so you aren't fitting all the parameters well, whereas b is just a single number. So almost all the parameters are in w rather than b, and if you add this last term, in practice it won't make much of a difference because b is just one parameter out of a very large number of parameters. In practice, I usually just don't bother to include it. but you can if you want. So L2 regularization is the most common type of regularization. You might have also heard of some people talk about L1 regularization, and that's when you add, instead of this L2 norm, you instead add a term that is lambda over m of sum over of this. And this is also called the L1 norm of the parameter vector w. So a little subscript 1 down there. Right? And I guess whether you put m or 2m in the denominator is just a scaling constant. If you use L1 regularization, then w will end up being sparse. And what that means is that the w vector will have a lot of zeros in it. And some people say that this can help with compressing the model, because if some parameters are 0, then you need less memory to store the model. Although I find that in practice, L1 regularization to make your model sparse helps only a little bit. So I don't think it's used that much, at least not for the purpose of compressing your model. And when people train neural networks, L2 regularization is just used much, much more often. Oh, sorry, just fixing up some of the notation here. So one last detail, lambda here is called the regularization parameter. And usually you set this using your development set or using holdout cross validation, where you try a variety of values and see what does the best in terms of trading off between doing well in your training set versus also setting the 2 norm of your parameters to be small, which helps prevent overfitting. So lambda is another hyperparameter that you might have to tune. And by the way, for the programming exercises, lambda is a reserved keyword in the Python programming language. So in the programming exercise, we'll have LAMBD without the A, so as not to clash with a reserved keyword in Python. So we'll use LAMBD to represent the lambda regularization parameter. So this is how you implement L2 regularization for logistic regression. How about a neural network? In a neural network, you have a cost function that's a function of all of your parameters, W1, B1 through W capital L, B capital L, where capital L is the number of layers in your neural network. And so the cost function is this, sum of the losses, summed over your M training examples. And so to add regularization, you add lambda over 2m of sum over all of your parameter W, your parameter matrices W, of their, let's call it the squared norm, where this norm of a matrix, really the squared norm, is defined as the sum over I, sum over j of each of the elements of that matrix squared. And if you want the indices of the summation, this is sum from I equals 1 through NL minus 1, sum from j equals 1 through NL, because W is a NL by NL minus 1 dimensional matrix, where these are the number of hidden units or number of units in layers L minus 1 and layer L. So this matrix norm, it turns out, is called the Frobenius norm of a matrix, denoted with F in the subscript. So for arcane linear algebra technical reasons, this is not called the L2 norm of a matrix. Instead, it's called the Frobenius norm of a matrix. I know it sounds like it'd be more natural just call the L2 norm of the matrix, but for really arcane reasons that you don't need to know, by convention, this is called the Frobenius norm, which just means the sum squared of elements of a matrix. So how do you implement gradient descent with this? Previously, we would compute dw, using backprop, where backprop would give us the partial derivative of j with respect to w, or well, really w for any given L. And then you update WL as WL minus the learning rate times d. So this was before we added this extra regularization term to the objective. Now that we've added this regularization term to the objective, what you do is you take dw and you add to it lambda over m times w. And then you just compute this update same as before. And it turns out that with this new definition of dwl, this is still, this new dwl is still a correct definition of the derivative of your cost function with respect to your parameters now that you've added the extra regularization term at the end. And it's for this reason that L2 regularization is sometimes also called weight decay. So if I take this definition of DWL and just plug it in here, then you see that the update is WL gets updated as WL times the learning rate alpha times, the thing from backprop, plus lambda over m times WL, so with a minus sign there. And so this is equal to WL minus alpha lambda over m times WL minus alpha times, the thing you got from backprop. And so this term shows that whatever the matrix WL is, you're going to make it a little bit smaller, right? This is actually as if you're taking the matrix W and you're multiplying it by 1 minus alpha lambda over m. You're really taking the matrix W and subtracting alpha lambda over m times it. So it's like you're multiplying the matrix W by this number, which is going to be a little bit less than 1. So this is why L2 norm regularization is also called weight decay, because it's just like the ordinary gradient descent, where you update W by subtracting alpha times the original gradient you got from backprop. But now you're also, multiplying W by this thing, which is a little bit less than 1. So the alternative name for L2 regularization is weight decay. I'm not really going to use that name, but the intuition for why it's called weight decay is that this first term here is equal to this. So you're just multiplying the weight matrix by a number slightly less than 1. So that's how you implement L2 regularization in a neural network. Now, one question that people sometimes ask me is, hey Andrew, why does regularization prevent overfitting? Let's take a quick look at the next video and gain some intuition for how regularization prevents overfitting. Why does regularization help with overfitting? Why does it help with reducing variance problems? Let's go through a couple examples to gain some intuition about how it works. So recall that our high bias, high variance, and just right pictures from an earlier video had looked something like this. Now let's say you're fitting a large and deep neural network. I know I haven't drawn this one too large or too deep, but let's say you're fitting some neural network and it's currently overfitting. So you have some cost function, right, J of WB equals sum of the losses, like so, right? And so what we did for regularization was add this extra term that penalizes the weight matrices from being too large. And we said that was a Frobenius norm. So why is it that shrinking the L2 norm or the Frobenius norm with the parameters might cause less overfitting? One piece of intuition is that if you crank the regularization lambda to be really, really big, they'll be really incentivized to set the weight matrices W to be reasonably close to 0. So one piece of intuition is maybe it'll set the weights to be so close to 0 for a lot of hidden units that is basically zeroing out a lot of the impact of these hidden units. And if that's the case, then this much simplified neural network becomes a much smaller neural network. In fact, it's almost like a logistic regression unit, but stacked multiple layers deep. And so that will take you from this overfitting case much closer to the left toward the high bias case. But hopefully there'll be an intermediate value of lambda that results in a result closer to this just right case in the middle. But the intuition is that by cranking up lambda to be really big, it'll set W close to 0, which in practice, this isn't actually what happens, but you can think of it as zeroing out, or at least reducing the impact of a lot of hidden units. So you end up with what might feel like a simpler network that gets closer and closer to as if you were just using logistic regression. The intuition of completely zeroing out a bunch of hidden units isn't quite right. It turns out that what actually happens is it'll still use all the hidden units, but each of them will just have a much smaller effect. But you do end up with a simpler network, and as if you have a smaller network that is therefore less prone to overfitting. So I'm not sure if this intuition helps, but when you implement regularization in the programming exercise, you actually see some of these variance reduction results yourself. Here's another attempt at additional intuition for why regularization helps prevent overfitting. And for this, I'm going to assume that we're using the tanh activation function, which looks like this, right? So this is a g of z equals tanh of z. So if that's the case, notice that so long as z is quite small, so if z takes on only a smallish range of parameters, maybe around here, then you're just using the linear regime of the tanh function. It's only if z is allowed to wander out, to larger values or smaller values like so, that the activation function starts to become less linear. So the intuition you might take away from this is that if lambda, the regularization parameter, is large, then you have that your parameters will be relatively small because they're penalized being large in the cost function. And so if the weights w are small, then because z is equal to w, right? And then technically it's buzz b. But if w tends to be very small, then z will also be relatively small. And in particular, if z ends up taking relatively small values just in this little range, then g of z will be roughly linear. So it's as if every layer will be roughly linear, as if it's just linear regression. And we saw in course 1 that if every layer is linear, then your whole network is just a linear network. And so even a very deep network, with a linear activation function, is at the end of the day only able to compute a linear function. So it's not able to fit those very, very complicated decision, very nonlinear decision boundaries that allow it to really overfit, right, the data set, like we saw on the overfitting high variance case on the previous slide. Okay, so just to summarize, if the regularization parameter is very large, the parameters w very small, so z will be relatively small, kind of ignoring the effects of b for now. But so z will be relatively small, or really, I should say it takes on a small range of values, and so the activation function, if it's tanh say, will be relatively linear, and so your whole neural network will be computing something not too far from a big linear function, which is therefore a pretty simple function rather than a very complex, highly nonlinear function. And so it's also much less able to overfit. Okay, and again, when you implement regularization for yourself in the programming exercise, you'll be able to see some of these effects yourself. Before wrapping up our discussion on regularization, I just want to give you one implementational tip, which is that when implementing regularization, we took our definition of the cost function j, and we actually modified it by adding this extra term that penalizes the weights being too large. And so if you implement gradient descent, one of the steps to debug gradient descent is to plot the cost function j as a function of the number of iterations of gradient descent, and you want to see that the cost function j decreases monotonically after every iteration of gradient descent. And if you're implementing regularization, then please remember that j now has this new definition. If you plot the old definition of j, just this first term, then you might not see it decrease monotonically. So to debug gradient descent, make sure that you're plotting this new definition of j that includes this second term as well. Otherwise, you might not see j decrease monotonically on every single iteration. So that's it for L2 regularization, which is actually a regularization technique that I use the most when training deep learning models. In deep learning, there's another sometimes used regularization technique called dropout regularization. Let's take a look at that in the next video. In addition to L2 regularization, another very powerful regularization technique is called dropout. Let's see how that works. Let's say you've trained a neural network like the one on the left and is overfitting. Here's what you do with dropout. Let me make a copy of the neural network. with Dropout, what we're going to do is go through each of the layers of the network and set some probability of eliminating a node in a neural network. So let's say that for each of these layers, we're going to, for each node, toss a coin and have a 0.5 chance of keeping each node and 0.5 chance of removing each node. So after the coin tosses, maybe we'll decide to eliminate those nodes. Then what you do is actually remove all the ingoing and outgoing links from that node as well. So you end up with a much smaller, really much diminished network. And then you do backpropagation, training this one example on this much diminished network. And then on a different example, you would toss a set of coins again and keep a different set of nodes, drop out or eliminate a different set of nodes. And so for each training example, you would train it using one of these reduced networks. So maybe this seems like a slightly crazy technique to just go around killing nodes at random, but this actually works. But you can imagine that because you're training a much smaller network on each example, maybe this gives a sense for why you end up able to regularize the network, because these much smaller networks are being trained. So let's look at how you implement Dropout. There are a few ways of implementing Dropout. I'm going to show you the most common one, which is a technique called inverted Dropout. For the sake of completeness, let's say we want to illustrate this with layer L equals 3. So in the code I'm going to write, there'll be a bunch of 3s here. That's just, that I'm just going to illustrate how to implement Dropout in a single layer. So what we're going to do is set a vector D, and D3 is going to be the dropout vector for layer 3. That's what the 3 is, to be np.random.rand, and this is going to be the same shape as A3. And I'm going to see if this is less than some number, which I'm going to call keep prob. And so keep prob is a number. It was 0.5 on the previous slide, but maybe now I'll use 0.8 in this example. And it'll be the probability that a given hidden unit will be kept. So if keep prob is equal to 0.8, then this means that there's a 0.2 chance of eliminating any hidden unit. So what this does is it generates a random matrix, and this works as well if you have vectorized. But so D3 will be a matrix where for each example and for each hidden unit, there's a 0.8 chance that the corresponding D3 will be 1, and a 20% chance that it'll be 0, right? So, this random number being less than 0.8, that has a 0.8 chance of being 1 or being true, and a 20% chance, a 0.2 chance of being false or being 0. And then what you're going to do is take your activations from the third layer, and just call it A3 in this little example. So A3 are the activations you computed, and you're going to set A3 to be equal to the old A3 times, okay, so this is element-wise multiplication, or I guess you could also write this as A3 times equals D3. But what this does is for every element of D3 that's equal to 0, and there was a 20% chance of each of the elements being 0, you end up, this multiply operation ends up zeroing out the corresponding element of D3. If you do this in Python, technically D3 will be a Boolean array with values true and false rather than 1 and 0, but the multiply operation works, and it'll interpret the true and false values as 1 and 0. If you try this yourself in Python, you'll see. Then finally, we're going to take A3 and scale it up by dividing by 0.8, or really dividing by our keep prob parameter. So let me explain what this final step is doing. Let's say for the sake of argument that you have 50 units or 50 neurons in the third hidden layer. So maybe A3 is 50 by 1 dimensional, or if you have vectorization, maybe it's 50 by m dimensional. So if you have a 80% chance of keeping and 20% chance of eliminating them, this means that on average you end up with 10 units, shut off, or 10 units zeroed out. And so now if you look at the value of Z4, Z4 is going to be equal to W4 times A3 plus B4. And so on expectation, this will be reduced by 20%, by which I mean that 20% of the elements of A3 will be zeroed out. So in order to not reduce the expected value of Z4, what you do is you need to take this and divide it by 0.8. Because this will, correct, or this will bump it back up by the roughly 20% that you need, so as to not change the expected value of A3. And so this line here is what's called the inverted dropout technique. And its effect is that no matter what you set the key prop to, whether it's 0.8 or 0.9 or even 1, if you set it to 1, then there's no dropout because you're keeping everything, or 0.5 or whatever. This inverted dropout technique, by dividing by the key prop, it ensures that the expected value of A3 remains the same. And it turns out that at test time, when you're trying to evaluate the neural network, which talked about on the next slide, this inverted dropout technique, there's this line that I drew the green box around, this makes test time easier because you have less of a scaling problem. But by far the most common implementation of dropout today, as far as I know, is inverted dropout. So I recommend you just implement this. But there were some early iterations of dropout that missed this divide by key prop line, and so at test time the algorithm became a little bit more complicated. But again, people tend not to use those other versions. So what you do is you use the D vector, and you notice that for different training examples, you zero out different hidden units. And in fact, if you make multiple passes through the same training set, then on different passes through the training set, you should randomly zero out different hidden units. So it's not that for one example, you should keep zeroing out the same hidden units, is that on iteration 1 of gradient descent, you might zero out some hidden units, and on the second iteration of gradient descent, where you go through the training set a second time, maybe you zero out a different pattern of hidden units. And the vector D, or D3 for the third layer, is used to decide what to zero out, both in forward prop as well as in back prop. We're just showing forward prop here. Now, having trained the algorithm, at test time, here's what you would do. At test time, you're given some X on which you want to make a prediction. And using our standard notation, I'm going to use A0, the activations of the 0th layer, to denote this test example X. So what we're going to do is not use dropout at test time. In particular, we're just going to set Z1 equals W1 A0 plus B1. A1 equals G1 of Z1. Z2 equals W2 A1 plus B2, A2 equals, and so on until you get to the last layer and then you make a prediction Y hat. But notice that at test time, you're not using dropout explicitly, in that you're not tossing coins at random, you're not flipping coins to decide which hidden units to eliminate. And that's because when you're making predictions at test time, you don't really want your output to be random. If you were implementing dropout at test time, that just adds noise to your predictions. In theory, one thing you could do is run a prediction process many times with different hidden units randomly dropped out and then average across them. But that's computationally inefficient, and it'll give you roughly the same result, very, very similar result to this particular procedure as well. And I just mentioned the inverted dropout thing. Remember the step on the previous slide where we divided by the keep prop. The effect of that was to ensure that even when you don't implement dropout at test time, to the scaling, the expected value of these activations don't change, so you don't need to add in an extra funny scaling parameter at test time that's different than what you had at training time. So that's dropout, and when you implement this in this week's primary exercise, you gain more first-hand experience with it as well. But why does it really work? What I want to do in the next video is give you some better intuition about what dropout really is doing. Let's go on to the next video. Dropout does this seemingly crazy thing of randomly knocking out units in your network. Why does it work so well as a regularizer? Let's gain some better intuition. In the previous video, I gave this intuition that dropout randomly knocks out units in your network, so it's as if on every iteration you're working with a smaller neural network, and so using a smaller neural network seems like it should have a regularizing effect. Here's a second intuition, which is, let's look at it from the perspective of a single unit. Right? Let's say this one. Now, for this unit to do its job, it has 4 inputs and it needs to generate some meaningful output. Now, with dropout, the inputs can get randomly eliminated. sometimes those two units would get eliminated, sometimes a different unit would get eliminated. So what this means is that this unit, which I'm circling in purple, it can't rely on any one feature, because any one feature could go away at random, or any one of its own inputs could go away at random. So in particular, it'll be reluctant to put all of its bets on, say, just this input, right? The weights, we're reluctant to put too much weight on any one input because it could go away. So this unit will be more motivated to spread out its weights and give you a little bit of weight to each of the four inputs to this unit. And by spreading out the weights, this will tend to have an effect of shrinking the squared norm of the weights. And so, similar to what we saw with L2 regularization, the effect of implementing dropout is that it shrinks the weights, and thus, similar to L2 regularization, it helps to prevent overfitting. But it turns out that dropout can formally be shown to be an adaptive form of L2 regularization, but the L2 penalty on different weights are different, depending on the size of the activations being multiplied into that weight. But to summarize, it is possible to show that dropout has a similar effect to L2 regularization. Only the L2 regularization applied to different weights can be a little bit different and even more adaptive to the scale of different inputs. One more detail for when you're implementing dropout. Here's a network where you have 3 input features. This is 7 hidden units here, 7, 3, 2, 1. So one of the parameters we had to choose was the keep prop, right, which is a chance of keeping a unit in each layer. So it is also feasible to vary keep prop by layer. So for the first layer, your matrix W1 will be 3 by 7. Your second weight matrix will be 7 by 7. W3 will be 7 by 3, and so on. And so W2 is actually the biggest weight matrix, right? Because they're actually the largest set of parameters will be in W2, which is 7 by 7. So to reduce overfitting of that matrix, maybe for this layer, I guess this is layer 2, you might have a keep prop that's relatively low, say 0.5. Whereas for different layers where you might worry less about overfitting, you could have a higher keep prop. Maybe this is 0.7, maybe this is 0.7. And then for layers where you don't worry about overfitting at all, you can have a keep prop of 1.0, right? So, for clarity, these are numbers I'm drawing in the purple boxes. These could be different keep props for different layers. Notice that the keep prop of 1.0 means that you're keeping every unit, and so you're really not using dropout for that layer. But for layers where you're more worried about overfitting, really the layers with a lot of parameters, you could set keep prop to be smaller to apply a more powerful form of dropout. It's kind of like cranking up the regularization parameter lambda for L2 regularization, where you try to regularize some layers more than others. And technically, you can also apply dropout to the input layer, where you can have some chance of, just Xing out one or more of the input features. Although in practice, usually don't do that often. And so a keep prop of 1.0 is quite common for the input layer. You might also use a very high value, maybe 0.9, but it's much less likely that, you want to eliminate half of the input features. So usually keep prop, if you apply it at all, will be a number close to 1, if you even apply dropout at all to the input layer. So just to summarize, if you're more worried about some layers overfitting than others, you can set a lower keep prop for some layers than others. The downside is this gives you even more hyperparameters to search for using cross-validation. One other alternative might be to have some layers where you apply dropout and some layers where you don't apply dropout, and then just have one hyperparameter, which is a keep prop for the layers for which you do apply dropout. And before we wrap up, just a couple implementational tips. Many of the first successful implementations of dropouts were to computer vision. So in computer vision, the input size is so big. You're inputting all these pixels that you almost never have enough data. And so dropout is very frequently used in computer vision. And there are some computer vision researchers that pretty much always use it, almost as a default. But really, the thing to remember is that dropout is a regularization technique. It helps prevent overfitting. And so unless my algorithm is overfitting, I wouldn't actually bother to use dropout. So it's used somewhat less often in other application areas. It's just if computer vision, you usually just don't have enough data, so you're almost always overfitting, which is why there tend to be some computer vision researchers that just swear by dropout. But the intuition doesn't always generalize, I think, to other disciplines. One big downside of dropout is that the cost function j is no longer well defined. On every iteration, you're randomly, killing off a bunch of nodes. And so if you're double checking the performance of gradient descent, it's actually harder to double check that, right? You have a well-defined cost function j that is going downhill on every iteration. Because the cost function j that you're optimizing is actually less well defined, or is certainly hard to calculate. So you lose this debugging tool to be able to plot a graph like this. So what I usually do is turn off dropout, or if you will, set key prop equals 1, and then run my code and make sure that it is monotonically decreasing j, and then turn on dropout and hope that, I didn't introduce a bug into my code during dropout, because you need other ways, I guess, but not plotting these figures to make sure that your code is working, the gradient descent is working, even with dropout. So with that, there's still a few more regularization techniques that are worth your knowing. Let's talk about a few more such techniques in the next video. In addition to L2 regularization and dropout regularization, there are a few other techniques for reducing overfitting in your neural network. Let's take a look. Let's say you're fitting a cat classifier. If you're overfitting, getting more training data can help, but getting more training data can be expensive, and you sometimes just can't get more data. But what you can do is augment your training set by taking an image like this, and for example, flipping it horizontally and adding that also to your training set. So now instead of just this one example in your training set, you can add this to your training example. So by flipping your images horizontally, you could maybe double the size of your training set. Because your training set is now a bit redundant, this isn't as good as if you had collected an additional set of brand new independent examples, but you could do this without needing to pay the expense of going out to make more pictures of cats. And then other than flipping horizontally, you can also take random crops of the image. So here we've rotated and sort of randomly zoom into the image, and this still looks like a cat. But so by taking random distortions and transformations of the image, you could augment your data set and make additional fake training examples. Again, these extra fake training examples, they don't add as much information as if you were to go out and get a brand new independent example of a cat. But because you could do this, almost for free, other than for some computational cost, this can be an inexpensive way to give your data. This can be an inexpensive way to give your algorithm more data, and therefore, sort of regularize it and reduce overfitting. And by synthesizing examples like this, what you're really telling your algorithm is that if something is a cat, then flipping it horizontally is still a cat. Notice I didn't flip it vertically because maybe we don't want upside down cats, right? And then also maybe randomly zooming into part of the image is probably still a cat. For optical character recognition, you can also augment your dataset by taking a digit and imposing random rotations and distortions to it. So if you add these things to your training set, these are also still digit 4s. For illustration, I applied a very strong distortion, so this looks like a very wavy 4. In practice, you don't need to distort the 4 quite as aggressively, but just a more subtle distortion than what I'm showing here to make this example clearer for you, right? But the more subtle distortion is usually used in practice because this looks like really warped 4s. So data augmentation can be used as a regularization technique, as effects similar to regularization. There's one other technique that is often used called early stopping. So what you're going to do is, as you run gradient descent, you're going to plot your either the training error, your 0-1 classification error on the training set, or just plot the cost function j you're optimizing, and that should decrease monotonically like so. Right? Because as you train, hopefully your training error or your cost function j should decrease. So with early stopping, what you do is you plot this, and you'd also plot your depth set error. And again, this could be a classification error on your development set, or something like the cost function, like the logistic loss or the log loss, evaluating our depth set. And what you find is that your depth set error will usually go down for a while, and then it will increase from there. So what early stopping does is you would say, well, it looks like your neural network was doing best around that iteration, so we're just going to stop training your neural network halfway and take whatever value achieved this depth set error. So why does this work? Well, when you haven't run many iterations for your neural network yet, your parameters W will be close to 0 because with random initialization, you probably initialize W to small random values. So before you train for a long time, W is still quite small. And as you iterate, as you train, W get bigger and bigger and bigger until here, maybe you have a much larger value of the parameters W for your neural network. So what early stopping does is by stopping halfway, you have only a mid-size, right, W. And so similar to L2 regularization, by picking a neural network with smaller norm for your parameters W, hopefully your neural network is overfitting less. And the term early stopping refers to the fact that you're just stopping the training of your neural network early. I sometimes use early stopping when training a neural network, but it does have one downside. Let me explain. I think of the machine learning process as comprising several different steps. One is that you want an algorithm to optimize the cost function J, and we have various tools to do that, such as gradient descent, and then we'll talk later about other algorithms like momentum and RMSprop and Atom and so on. But then after optimizing the cost function J, you also want it to not overfit. And we have some tools to do that, such as regularization, getting more data, and so on. Now, in machine learning, we already have so many hyperparameters to search over. It's already very complicated to choose among the space of possible algorithms. And so I find machine learning easier to think about when you have one set of tools for optimizing the cost function J. And when you're focusing on optimizing the cost function J, all you care about is finding W and B so that J of W and B is as small as possible. You just don't think about anything else other than reducing this. And then it's a completely separate task to not overfit. In other words, to reduce variance. And when you're doing that, you have a separate set of tools for doing it. And this principle is sometimes called orthogonalization. And this is the idea that you want to be able to think about one task at a time. I'll say more about orthogonalization in a later video. So if you don't fully get the concept yet, don't worry about it. But to me, the main downside of early stopping is that this couples these two tasks. So you no longer can work on these two problems independently. Because by stopping gradient descent early, you're sort of breaking whatever you're doing to optimize the cost function J, because now you're not doing a great job reducing the cost function J. You've sort of not done that well. And then you're also simultaneously trying to not overfit. So instead of using different tools to solve the two problems, you're using one tool that kind of mixes the two. And this just makes the set of things you could try more complicated to think about. Rather than using early stopping, one alternative is just use L2 regularization. Then you can just train the neural network as long as possible. I find that this makes the search space of hyperparameters easier to decompose and easier to search over. But the downside of this, though, is that you might have to try a lot of values of the regularization parameter lambda. And so this makes searching over many values of lambda more computationally expensive. And the real advantage of early stopping is that running the gradient descent process just once, you get to try out values of small w, mid-size w, and large w without needing to try a lot of values of the regularization, L2 regularization hyperparameter lambda. If this concept doesn't completely make sense to you yet, don't worry about it. When we talk about orthogonalization in greater detail in a later video, I think this will make a bit more sense. Despite its disadvantages, many people do use it. I personally prefer to just use L2 regularization and try different values of lambda. That's assuming you can afford the computation to do so. But early stopping does let you get a similar effect without needing to explicitly try lots of different values of lambda. So you've now seen how to use data augmentation, as well as, if you wish, early stopping in order to reduce variance or to prevent overfitting in your neural network. Next, let's talk about some techniques for setting up your optimization problem to make your training go quickly. When training a neural network, one of the techniques that will speed up your training is if you normalize your inputs. Let's see what that means. Let's see if a training set with two input features. So the input features x are two-dimensional, and here's a scatter plot of your training set. Normalizing your inputs corresponds to two steps. The first is to subtract out or to zero out the mean. So you set mu equals 1 over m sum over I of xi. So this is a vector, and then x gets set as x minus mu for every training example. So this means you just move the training set until it has zero mean. And then the second step is to normalize the variances. So notice here that the feature x1 has a much larger variance than the feature x2 here. So what we do is set sigma equals 1 over m sum of xi star star 2. I guess this is element-wise squaring. And so now sigma squared is a vector with the variances of each of the features. And notice we've already subtracted out the mean. So xi squared, element-wise squared, is just the variances. And you take each example and divide it by this vector, sigma squared. And so in pictures, you end up with this, where now the variance of x1 and x2 are both equal to 1. Oh, and one tip, if you use this to scale your training data, then use the same mu and sigma squared to normalize your test set, right? In particular, you don't want to normalize the training set and the test set differently. Whatever this value is and whatever this value is, use them in, these two formulas so that you scale your test set in exactly the same way rather than estimating mu and sigma squared separately on your training set and test set. Because you want your data, both training and test examples, to go through the same transformation defined by the same mu and sigma squared calculated on your training data. So why do we do this? Why do we want to normalize the input features? Recall that the cost function is defined as written on the top right. It turns out that if you use unnormalized input features, it's more likely that your cost function will look like this, like a very squished out bow, a very elongated cost function, where the minimum you're trying to find is maybe over there. But if your features are on very different scales, say the feature x1 ranges from 1 to 1000 and the feature x2 ranges from 0 to 1, then it turns out that the ratio or the range of values for the parameters W1 and W2 will end up taking on very different values. And so maybe these axes should be W1 and W2, but with intuition, I'll plot W and B. But your cost function can be a very elongated bow like that. So if you plot the contours of this function, you can have a very elongated function like that. Whereas if you normalize the features, then your cost function will on average look more symmetric. And if you're running gradient descent on the cost function like the one on the left, then you might have to use a very small learning rate, because if you're here, then gradient descent might need a lot of steps to oscillate back and forth, right, before it finally finds its way to the minimum. Whereas if you have a more spherical contours, then wherever you start, gradient descent can pretty much go straight to the minimum. You can take much larger steps with gradient descent rather than needing to oscillate around like the picture on the left. Of course, in practice, W is a high dimensional vector, and so trying to plot this in 2D doesn't convey all the intuitions correctly. But the rough intuition that your cost function will be more round and easier to optimize when your features are all on similar scales, not from 1 to 1000, 0 to 1, but mostly from minus 1 to 1 or with about similar variance as each other. That just makes your cost function J easier and faster to optimize. In practice, if one feature, say x1, ranges from 0 to 1, and x2 ranges from minus 1 to 1, and x3 ranges from 1 to 2, these are fairly similar ranges, so this will work just fine, is when they're on dramatically different ranges, like one's from 1 to 1,000 and another from 0 to 1, that really hurts your optimization algorithm. But by just setting all of them to 0 mean and say variance 1, like we did on the last slide, that just guarantees that all your features are a similar scale and will usually help your learning algorithm run faster. So if your input features came from very different scales, maybe some features are from 0 to 1, some from 1 to 1,000, then it's important to normalize your features. If your features came in on similar scales, then this step is less important, although performing this type of normalization pretty much never does any harm, so I'll often do it anyway if I'm not sure whether or not it'll help with speeding up training for your algorithm. So that's it for normalizing your input features. Next, let's keep talking about ways to speed up the training of your neural network. One of the problems with training neural networks, especially very deep neural networks, is that of vanishing and exploding gradients. What that means is that when you're training a very deep network, your derivatives or your slopes can sometimes get either very, very big or very, very small, maybe even exponentially small, and this makes training difficult. In this video, you see what this problem of exploding and vanishing gradients really means, as well as how you can use careful choices of the random weight initialization to significantly reduce this problem. Let's say you're training a very deep neural network like this. To save space on this slide, I've drawn it as if you have only 2 hidden units per layer, but it could be more as well. But this neural network will have parameters W1, W2, W3, and so on up to WL. For the sake of simplicity, let's say we're using an activation function g of z equals z, so a linear activation function, and let's ignore b. Let's set b of l equals 0. So in that case, you can show that the output y will be wl times wl minus 1 times wl minus 2 ... down to w3, w2, w1 times x. But if you want to just check my math, w1 times x is going to be z1, right? Because b is equal to 0, so z1 is equal to, I guess, w1 times x, and then plus b, which is 0. But then a1 is equal to g of z1, but because we use a linear activation function, this is just equal to z1. So this first term, w1x, is equal to a1. And then by similar reasoning, you can figure out that w2 times w1 times x is equal to a2, because that's going to be g of z2 is going to be g of w2 times a1, right? Which you plug that in here. So this thing is going to be equal to a2, and then this thing is going to be a3, and so on until the product of all of these matrices gives you y hat, not y. Now let's say that each of your weight matrices wl is equal to, let's say it's just a little bit larger than 1 times the identity. So it's 1.5, 1.5, 0, 0. Right? Technically, the last one has different dimensions, so maybe this is just the rest of these weight matrices. Then y hat will be, ignoring this last one, which is different dimension, will be this 1.5, 0, 0, 1.5 matrix to the power of L minus 1 times x, because if we assume that each one of these matrices, is equal to this thing, it's really 1.5 times the identity matrix, then you end up with this calculation. And so y hat will be essentially 1.5 to the power of L, to the power of L, L minus 1 times x. And if L is large for a very deep neural network, y hat will be very large. In fact, this grows exponentially. It grows like 1.5 to the number of layers. And so if you have a very deep neural network, the value of y will explode. Now conversely, if we replace this with 0.5, so something less than 1, then this becomes 0.5 to the power of L, right? This matrix becomes 0.5 to the L minus 1 times x, again ignoring WL. But so if each of your matrices are less than 1, then if, let's say x1, x2 were 1, 1, then the activations would be 1/2, 1/2, 1/4, 1/4, 1/8, 1/8, and so on until this becomes 1 over 2 to the L. So the activation values will decrease exponentially as a function of the depth, as a function of the number of layers L of the network. So if you have a very deep network, the activations end up decreasing exponentially. So the intuition I hope you can take away from this is that if the weights, W, if they're all, just a little bit bigger than 1, or just a little bit bigger than the identity matrix, then with a very deep network, the activations can explode. And if W is, just a little bit less identity, right? So if this was maybe is 0.9, 0.9, right? Then if a very deep network, the activations will decrease exponentially. And even though I went through this argument in terms of activations increasing or decreasing exponentially as a function of L, a similar argument can be used to show that the derivatives or the gradients you compute with gradient descent will also increase exponentially or decrease exponentially as a function of the number of layers. With some of the modern neural networks, you actually have L equals 150. Microsoft recently got great results of, I think, 152-layer neural network. But with such a deep neural networks, if your activations, your gradients increase or decrease exponentially as a function of L, then these values could get really big or really small. And this makes training difficult, especially if your gradients are exponentially small in L, then, gradient descent will take tiny little steps and it'll take a long time for gradient descent to learn anything. To summarize, you've seen how deep networks suffer from the problems of vanishing or exploding gradients. In fact, for a long time, this problem was a huge barrier to training deep neural networks. It turns out there's a partial solution that doesn't completely solve this problem, but that helps a lot, which is careful choice of how you initialize the weights. To see that, let's go on to the next video. In the last video, you saw how very deep neural networks can have the problems of vanishing and exploding gradients. It turns out that a partial solution to this, doesn't solve it entirely, but helps a lot, is better or more careful choice of the random initialization for your neural network. To understand this, let's start with the example of initializing the weights for a single neuron, and then we'll go on to generalize this to a deep network. Let's go through this with an example with just a single neuron, and then we'll talk about a deep net later. So with a single neuron, you might input 4 features, x1 through x4, and then you have some a equals g of z, and then it outputs some y. And later on, for a deeper net, these inputs will be, some layer a of L. But for now, let's just call this x for now. So z is going to be equal to w1 x1 plus w2 x2 plus ... plus, I guess, wn xn. And let's set b equals 0. So, let's just ignore b for now. So in order to make z not blow up and not become too small, you notice that the larger n is, the smaller you want wi to be, right? Because z is a sum of wi xi, and so if you're adding up a lot of these terms, you want each of these terms to be smaller. One reasonable thing to do would be to set the variance of wi to be equal to 1 over n, where n is the number of input features that's going into a neuron. So in practice, what you can do is set the weight matrix W for a certain layer to be np dot random dot rand n, and then whatever the shape of the matrix is, you fill this out here, and then times square root of 1 over the number of features that are fed into each neuron in layer L. So it's going to be n of L minus 1, because that's the number of units that are feeding in to each of the units in layer L. It turns out that if you're using a ReLU activation function, then rather than 1 over n, it turns out that setting the variance to 2 over n works a little bit better. So you often see that in initialization, especially if you're using a ReLU activation function. So if GL of z is ReLU of z. Oh, and depending on how familiar you are with random variables, it turns out that sampling a Gaussian random variable and then multiplying it by square root of this, that sets the variance to be equal to this thing, to be 2 over n. Okay, and the reason I went from n to this n superscript L minus 1 was in this example with logistic regression, which is at n input features, but in the more general case, layer L would have n L minus 1 inputs, each of the units in that layer. So if the input features or the input activations are roughly mean 0 and standard variance and variance 1, then this will cause Z to also take on a similar scale. And this doesn't solve, but it definitely helps reduce the vanishing and exploding gradients problem, because it's trying to set each of the weight matrices W, so that it's not too much bigger than 1 and not too much less than 1, so it doesn't explode or vanish too quickly. I'll just mention some other variants. The version we just described is assuming a ReLU activation function, and is by a paper by He et al. A few other variants, if you are using a tanh activation function, then there's a paper that shows that instead of using the constant 2, it's better to use the constant 1. And so 1 over this instead of 2. And so you multiply by the square root of this. So this square root term would replace this term. And you use this if you're using a tanh activation function. This is called Xavier initialization. And another version worked out by Yoshua, Bengio, and his colleagues, you might see in some papers, but is to use this formula, which has some other theoretical justification. But I would say if you're using a ReLU activation function, which is really the most common activation function, I would use this formula. If you're using tanh, you could try this version instead, and some authors will also use this. But in practice, I think all of these formulas just give you a starting point. It gives you a default value to use for the variance of the initialization of your weight matrices. If you wish, the variance here, this variance parameter, could be another thing that you could tune with your hyperparameters. So you could have another parameter that multiplies into this formula and tune that multiplier as part of your hyperparameter search. Sometimes the tuning that hyperparameter has a modest size effect. It's not one of the first hyperparameters I would usually try to tune, but I've also seen some problems where tuning this helps a reasonable amount. But this is usually lower down for me in terms of how important it is relative to the other hyperparameters you could tune. So I hope that gives you some intuition about the problem of vanishing or exploding gradients, as well as how choosing a reasonable scaling for how you initialize the weights. Hopefully that makes your weights not explode too quickly and not decay to 0 too quickly, so you can train a reasonably deep network without the weights or the gradients exploding or vanishing too much. When you train deep networks, this is another trick that will help you make your neural networks train much more quickly. When you implement backpropagation, you find that there's a test called gradient checking that can really help you make sure that your implementation of backprop is correct. Because sometimes you write all these equations and you're just not 100% sure if you got all the details right in implementing backpropagation. So in order to build up to gradient checking, let's first talk about how to numerically approximate computations of gradients. And then in the next video, we'll talk about how you can implement gradient checking to make sure that your implementation of backprop is correct. So let's take the function f and replot it here. And remember, this is f of theta equals theta cubed. And let's again start off with some value of theta. Let's say theta equals 1. Now, instead of just nudging theta to the right to get theta plus epsilon, we're going to nudge it to the right and nudge it to the left to get theta minus epsilon, as well as theta plus epsilon. So this is 1, this is 1.01, this is 0.99, where again epsilon is same as before, is 0.01. It turns out that rather than taking this little triangle and computing the height over the width, you can get a much better estimate of the gradient if you take this point, f at theta minus epsilon, and this point, and you instead compute the height over width of this bigger triangle. So for technical reasons, which I won't go into, the height over width of this bigger green triangle gives you a much better approximation to the derivative at theta. And you want, sort of instead of taking just this little triangle on the upper right, is as if you have two triangles, right? This one on the upper right and this one on the lower left, and you're kind of taking both of them into account by using this bigger green triangle. So rather than a one-sided difference, you're taking a two-sided difference. So let's work on the math. This point here is f of theta plus epsilon. This point here is f of theta minus epsilon. So the height of this big green triangle is f of theta plus epsilon minus f of theta minus epsilon. And then the width, this is 1 epsilon, this is 2 epsilon, so the width of this green triangle is 2 epsilon. So the height over width is going to be first the height, so that's f of theta plus epsilon minus f of theta minus epsilon, divided by the width, so that was 2 epsilon, which we worked out down here. And this should hopefully be close to g of theta. So plugging in the values, remember f of theta is theta cubed, so this is theta plus epsilon is 1.01. So take the cube of that minus, now 0.99, take the cube of that, divided by 2 times 0.01. Feel free to pause the video and plug this in the calculator. You should get that this is 3.0001. Whereas from the previous slide, we saw that g of theta, this was 3 theta squared, so when theta equals 1, this is... So these two values are actually very close to each other. The approximation error is now 0.0001. Whereas on the previous slide, with taking the one-sided difference, just theta and theta plus epsilon, we had gotten 3.0301, and so the approximation error was 0.03, right, rather than 0.0001. But so with this two-sided difference way of approximating the derivative, you find that this is extremely close to 3, and so this gives you, much greater confidence that g of theta is probably a correct implementation of the derivative of f. When you use this method for gradient checking and backpropagation, this turns out to run twice as slow as you were to use a one-sided difference. It turns out that in practice, I think it's worth it to use this other method because it's just much more accurate. Little bit of optional theory for those of you that are a little bit more familiar with calculus. It turns out that, and it's okay if you don't get what I'm about to say here, but it turns out that the formal definition of a derivative is for very small values of epsilon is f of theta plus epsilon minus f of theta minus epsilon over 2 epsilon. And the formal definition of a derivative is in the limit of exactly that formula on the right as epsilon goes to 0. And the definition of a limit is something that you learn if you take a calculus class, but I won't go into that here. And it turns out that for a non-zero value of epsilon, you could show that the error of this approximation is on the order of epsilon squared. And remember, epsilon is a very small number. So if epsilon is 0.01, which it is here, then epsilon squared is 0.0001. The big O notation means the error is actually some constant times this, but this is actually exactly our approximation error. So the big O constant happened to be 1. Whereas in contrast, if we were to use this formula, the other one, then the error is on the order of epsilon. And again, when epsilon is a number less than 1, then epsilon is actually much bigger than epsilon squared, which is why this formula here is actually a much less accurate approximation than this formula on the left, which is why when doing gradient checking, we rather use this two-sided difference where you compute f of theta plus epsilon minus f of theta minus epsilon, and then divide by 2 epsilon, rather than this one-sided difference, which is less accurate. If you didn't understand my last few comments, all of these things down here, don't worry about it. That's really more for those of you that are a bit more familiar with calculus and with numerical approximations. But the takeaway is that this two-sided difference formula is much more accurate, and so that's what we're going to use when we do gradient checking in the next video. So you've seen how by taking a two-sided difference, you can numerically verify whether or not a function g of theta that someone else gives you is a correct implementation of the derivative of a function f. Let's now see how we can use this to verify whether or not your backpropagation implementation is correct, or if there might be a bug in there that you need to go in and tease out. Gradient checking is a technique that's helped me save tons of time and helped me find bugs in my implementations of backpropagation many times. Let's see how you could use it too to debug or to verify that your implementation of backprop is correct. So your neural network will have some set of parameters, W1, B1, and so on up to WL, BL. So to implement gradient checking, the first thing you should do is take all your parameters and reshape them into a giant vector theta. So what you should do is take W, which is a matrix, and reshape it into a vector. Take all of these W's and reshape them into vectors, and then concatenate all of these things so that you have a giant vector theta, giant vector parameters theta. So instead of a cost function, J, being a function of the W's and B's, you would now have the cost function J being just a function of theta. Next, with W and B ordered the same way, you can also take dW1, dB1, and so on, and reshape them into big giant vector d theta of the same dimension as theta. Right? So same as before, reshape dW1 into a matrix, dB1 is already a vector, reshape dWL, all the dWs which are matrices. Remember, dW1 has the same dimension as W1, dB1 has the same dimension as B1. So with the same sort of reshaping and concatenation operation, you can then reshape all of these derivatives into a giant vector d theta, which is the same dimension as theta. So the question is now, is d theta the gradient or the slope of the cost function J? So here's how you implement gradient checking, and often abbreviate gradient checking to grad check. So first remember that J is now a function of the giant parameter theta, right? So you can also expand this out to J is a function of theta 1, theta 2, theta 3, and so on, right? Whatever is the dimension of this giant parameter vector theta. So to implement grad check, what you're going to do is implement a loop so that for each I, so for each component of theta, let's compute d theta approx I to b, and we're going to take a two-sided difference. We're going to take j of theta, theta 1, theta 2, up to theta I, and we're going to nudge theta I to add epsilon to this. So just, increase theta I by epsilon and keep everything else the same. And because we're taking a two-sided difference, we're going to do the same on the other side with theta I, but now minus epsilon. And then all of the other elements of theta are left alone. And then we'll take this and we'll divide it by 2 theta. And what we saw from the previous video is that this should be approximately equal to d theta I, which is supposed to be the partial derivative of J with respect to, I guess, theta I, if d theta I is, the derivative of the cost function J. So what you're going to do is you're going to compute this for every value of I, and at the end, you now end up with 2 vectors. You end up with this d theta approx, and this is going to be the same dimension as d theta, and both of these are in turn the same dimension as theta. And what you want to do is check if these vectors are approximately equal to each other. So in detail, well, how do you define whether or not 2 vectors are really reasonably close to each other? What I do is the following. I would compute the Euclidean distance between these 2 vectors, d theta approx minus d theta, so just the L2 norm of this. Notice there's no square on top, so this is the sum of squares of elements of the differences, and then you take a square root to actually get the Euclidean distance. And then just to normalize by the lengths of these vectors, I divide by d theta approx plus d theta. Just take the Euclidean lengths of these vectors. And the rho for the denominator is just in case any of these vectors are really small or really large, the denominator turns this formula into a ratio. So when you implement this in practice, I use epsilon equals maybe 10 to the minus 7, so 1e minus 7. And with this range of epsilon, if you find that this formula gives you a value like 10 to the minus 7 or smaller, then that's great. It means that your derivative approximation is very likely correct. This is just very small value. If it's maybe on the range of 10 to the minus 5, I would take a careful look. Maybe this is okay. But I might double check the components of this vector and make sure that none of the components are too large. And if some of the components of this difference are very large, then maybe you have a bug somewhere. And if this formula on the left is, on the order of 10 to the minus 3, then I would worry. I would be much more concerned that maybe there's a bug somewhere. But you should really be getting values much smaller than 10 to the minus 3. And if it's any bigger than 10 to the minus 3, then I would be quite concerned. I would seriously worry about whether or not there's a bug. And I would then, you should then look at the individual components of theta to see, if there's a specific value of I for which d theta approx I is very different from d theta I, and use that to try to track down whether or not some of your derivative computations might be incorrect. And after some amount of debugging, if finally it ends up being this kind of very small value, then you probably have a correct implementation. So when implementing a neural network, what often happens is I'll implement forward prop, implement back prop, and then I might find that this grad check gives a relatively big value, and then I would suspect that it must be a bug. Go in, debug, 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 and after debugging for a while, if I find that it parses grad check with a small value, then you can be much more confident that it's then correct. So you now know how gradient checking works. This has helped me find lots of bugs in my implementations of neural nets, and I hope it'll help you too. In the next video, I want to share with you some tips or some notes on how to actually implement gradient checking. Let's go on to the next video. In the last video, you learned about gradient checking. In this video, I want to share with you some practical tips or some notes on how to actually go about implementing this for your neural network. First, don't use grad check in training, only to debug. So what I mean is that computing d theta approx I for all the values of I, this is a very slow computation. So to implement gradient descent, you should use backprop to compute d theta and just use backprop to compute the derivative. And it's only when you're debugging that you would compute this to make sure it's close to d theta. But once you've done that, then you would turn off the grad check and don't run this during every iteration of gradient descent because that's just much too slow. Second, if an algorithm fails grad check, look at the components, look at the individual components to try to identify the bug. So what I mean by that is if d theta approx is very far from d theta, what I would do is look at the different values of I to see which are the values of d theta approx that are really very different than the values of d theta. So for example, if you find that the values of theta or d theta, they're very far off, all correspond to dBl for some layer or for some layers, but the components for dW are quite close, right? Remember, different components of theta correspond to different components of B and W. When you find this is the case, then maybe you find that the bug is in how you're computing dB, the derivative with respect to parameters B. And similarly, vice versa. If you find that the values that are very far, the values from d theta approx that are very far from d theta, if you find that all those components came from dW or from dW in a certain layer, then that might help you hone in on the location of the bug. This doesn't always let you identify the bug right away, but sometimes it helps you give you some guesses about where to track down the bug. Next, when doing grad check, remember your regularization term if you're using regularization. So if your cost function is j of theta equals 1 over m sum of your losses, and then plus this regularization term, right, sum of L of WL for obedience norm squared, then this is the definition of j. And you should have that d theta is gradient of j with respect to theta, including this regularization term. So just remember to include that term. Next, grad check doesn't work with dropout because in every iteration, dropout is randomly eliminating different subsets of the hidden units. There isn't a easy to compute cost function j that dropout is doing gradient descent on. It turns out that dropout can be viewed as optimizing some cost function j, but it's cost function j defined by summing over all exponentially large subsets of nodes it could eliminate in any iteration. So the cost function j is very difficult to compute, and you're just sampling the cost function every time you eliminate a different random subset of nodes when you use dropout. So it's difficult to use grad check to double check your computation with dropouts. So what I usually do is implement grad check without dropout. So if you want, you can set heap prop in dropout to be equal to 1.0, and then turn on dropout and hope that my implementation of dropout was correct. There are some other things you could do, like fix the pattern of nodes dropped and verify that grad check for that pattern of units killed off is correct, but in practice, I don't usually do that. So my recommendation is turn off dropout, use grad check to double check that your algorithm is at least correct without dropout, and then turn on dropout. Finally, this is a subtlety. It is not impossible, rarely happens, but it's not impossible that your implementation of gradient descent is correct when W and B are close to 0, so at random initialization, but that as you run gradient descent and W and B become bigger, maybe your implementation of backprop is correct only when W and B is close to 0, but it gets more inaccurate when W and B become large. So one thing you could do, I don't do this very often, but one thing you could do is run grad check at random initialization and then train the network for a while so that W and B have some time to wander away from 0, from your small random initial values, and then run grad check again after you've trained for some number of iterations. So that's it for gradient checking, and congratulations for coming to the end of this week's materials. In this week, you've learned about how to set up your train, depth, and test sets, how to analyze bias and variance, and what things to do if you have high bias versus high variance versus maybe high bias and high variance. You also saw how to apply different forms of regularization, like L2 regularization and dropout on your neural network. Saw some tricks for speeding up the training of your neural network, and then finally, gradient checking. So I think you've seen a lot in this week, and you get to exercise a lot of these ideas in this week's programming exercise. So best of luck with that, and I look forward to seeing you in the week 2 materials. Hi, Yoshua. I'm really glad you could join us here today.
Oh, I'm very glad too.
You know, today you're not just a researcher or engineer in deep learning, you've become one of the institutions or one of the icons of deep learning. But I'd really like to hear the story of how it started. So how did you end up, getting into deep learning and then pursuing this journey?
Right. Well, actually, it started when I was a kid, adolescent, reading a lot of science fiction, like I guess many of us. And when I started my graduate studies in 1985, I started reading neural net papers, and that's where I got all excited, and it became really a passion.
And actually, what was that like in mid 80s, right? 1985, reading these papers. Do you remember?
Yeah, it was well, coming from the courses I had taken in classical AI with expert systems, and suddenly discovering that there was all this world of thinking about how humans might be learning and human intelligence, and how we might draw connections between that and artificial intelligence and computers. That was really exciting for me when I discovered this literature, and I started reading the connectionists, of course, so the papers from Jeff Hinton, Rumelhart, and so on. And I worked on recurrent nets. I worked on speech recognition. I worked on HMMs, so graphical models, and then quickly moved to AT&T, Bell Labs, and MIT, where I did postdocs. And that's where I discovered some of the issues with the long-term dependencies with training neural nets. And then shortly after, I got recruited at UDM back in Montreal, where I had spent most of my adolescence years.
And so as someone who's been there for the last several decades and seen it all, or certainly seen a lot of it, tell me a bit about how your thinking about deep learning, about neural networks has evolved over this time.
We start with experiments, with intuitions, and theory sort of comes later. And we now understand a lot better, for example, why backprop is working so well, why depth is so important. And these kinds of notions we didn't have any solid justification for in those days. When we started working on deep nets in the early 2000s, we had the intuition that it made a lot of sense that a deeper network should be more powerful, and we didn't know how to take that and improve it. And of course, our experiments initially didn't work.
And actually, what were the most important things that you think turned out to be right, and what were the biggest surprises of what turned out to be wrong, compared to what we knew 30 years ago?
Oh, sure. So one of the biggest mistake I made was to think that, like everyone else in the 90s, that you needed smooth nonlinearities in order to for backprop to work. Because I thought that if we had something like the rectifying nonlinearities where you have a flat part, that it would be really hard to train because the derivative would be zero in so many places. And when we started experimenting with ReLU with deep nets in around 2010, I was obsessed with the idea that, we should be careful about whether neurons won't saturate too much on the zero part. But in the end, it turned out that actually the ReLU was working a lot better than the sigmoids and the tanh. And that was a big surprise. We did this, exploring this because of the biological connection, actually, not because we thought that it would be easier to optimize, but it turned out to work better, whereas I thought it would be harder to train.
So let me ask you, what is the relationship between deep learning and the brain? There's the obvious answer, but I'm curious, what's your answer to that?
Well, the initial insight that really got me excited with neural nets was this idea from the connectionists that information is distributed across the activation of many neurons rather than being represented by sort of the grandmother cell, as they were calling it, where a symbolic representation that was the traditional view in classical AI. And I still believe this is a really important thing, and I see people rediscovering the importance of that even recently. So that was really a foundation. The depth thing is something that came later in the early 2000s, but it wasn't something I was thinking about in the 90s, for example.
Right, right. I remember you built a lot of relatively shallow but very distributed representations for the word embeddings, right, very early on.
That's right. That's right. Yeah, that's one of the things that I got really excited about in the late 90s with actually my brother Semi and I worked on the idea that we could use neural nets to tackle the curse of dimensionality, which was believed to be one of the central issues with statistical learning. And the fact that we could have these distributed representations could be used to represent joint distributions over many random variables in a very efficient way. And it turned out to work quite well. And then I extended this to joint distributions over sequences of words. And this is how the word embeddings were born, because I thought, this will allow generalization across words that have similar semantic meaning and so on.
So over the last couple decades, your research group has invented more ideas than anyone can summarize in a few minutes. So I'm curious, what are the inventions or ideas you're most proud of from your group?
Right. So I think I mentioned long-term dependencies, the study of that. I think people still don't understand it well enough. Then there's the story I mentioned about curse of dimensionality, joint distributions with neural nets, which became more recently the NAID that Hugo La Rochelle did. And then, as I said, that gave rise to also the work on learning word embeddings for joint distributions over words. Then came, I think, probably the best known events of the work we did with deep learning, with stacks of autoencoders and stacks of RBMs. One thing then it was the work on understanding better the difficulties of training deep nets with Xavier Loro with the initialization ideas and also the vanishing gradient in deep nets. And that work actually was the one which gave rise to the experiments showing the importance of piecewise linear activation functions. Then I would say some of the most important work regards the work we did with unsupervised learning, the denoising autoencoders, the GANs, which are very popular these days, the generative adversarial networks. The work we did with neural machine translation using attention, which turned out to be really important for making translation work, and is currently used in industrial systems like Google Translate. But this attention thing actually really changed my views on neural nets. Neural nets we used to think as machines that can map a vector to a vector. But really, with attention mechanisms, you can now handle any kind of data structure, and this is really opening up a lot of interesting avenues. Direction of actually connecting to biology, one thing that I've been working on in the last couple of years is how could we come up with something like backprop, but that brains could implement. And we have a few papers in that direction that seems to be interesting for the neuroscience people. And then we're continuing on that direction, of course.
One of the topics that I know you've been thinking a lot about is the relationship between deep learning and the brain. Can you tell us a bit more about that?
The biological thing is something I've been thinking about for a while, actually, and having a lot of I would say daydreaming about, because it's like I think of it like a puzzle. So we have these pieces of evidence from what we know from the brain and from learning in the brain, like spike timing dependent plasticity, and on the other hand, we have all of these concepts from machine learning, the idea of globally training the whole system with respect to an objective function, and the idea of backprop, and what does backprop mean? Like, what does credit assignment really mean? When I started thinking about how brains could do something like backprop, it prompted me to think about, well, maybe there's like some more general concepts behind backprop which make it so efficient, which allow us to be efficient with backprop. Maybe there's a larger family of ways to do credit assignment, and that connects to questions that people in reinforcement learning have been asking. So it's interesting how sometimes asking a simple question leads you to thinking about so many different things, and forces you to think about so many elements that you like to bring together like a big puzzle. So this has gone for a number of years. I need to say that this whole endeavor, like many of the ones that I've followed, has been highly inspired by Jeff Hinton's thoughts. So in particular, he gave this talk in 2007, I think, the first deep learning workshop on what he thought was the way that the brain is working, how temporal code could be used for potentially doing some of the job of backprop, and that led to a lot of the ideas that I've explored in recent years with this. So it's kind of an interesting story that has been running for a decade now, basically.
One of the topics I've heard you speak about multiple times as well is unsupervised learning.
Yes.
Can you share your perspective on that?
Yes. So unsupervised learning is really important. Right now, our industrial systems are based on supervised learning, which essentially requires humans to define what the important concepts are for the problem and to label those concepts in the data. We build all these amazing toys and services and systems using this. But humans are able to do much more. They're able to explore and discover new concepts by observation and interaction with the world. A 2-year-old is able to understand intuitive physics. In other words, she understands gravity, she understands pressure, she understands inertia, she understands liquids, solids, and of course, her parents never told her about any of these stuff, right? So how did she figure it out? So that's the kind of question that unsupervised learning is trying to answer. It's not just about we have labels or we don't have labels. It's about actually building a construction, a mental construction that explains how the world works by observation. And more recently, I've been combining the ideas in unsupervised learning with the ideas in reinforcement learning, because I believe that there's a very strong indication about the important underlying concepts
that we're trying to disentangle, we're trying to separate from each other, that a human or machine can get by interacting with the world, by exploring the world and trying things and trying to control things. So these are, I think, tightly coupled to the original ideas of unsupervised learning. So my take on unsupervised learning 15 years ago, when we started doing the autoencoders and the RBMs and so on, was very focused on the idea of learning good representations, and I still think this is a central question. But the thing we don't know is how, what is a good representation? How do we figure out an objective function, for example? So we've tried many things over the years, and that's actually one of the cool things about unsupervised learning research, that there are so many different ideas, so different ways that this problem can be attacked, and that suggests maybe there's another one we'll discover, next year, that's completely different, and maybe the brain is using something else completely different. So it's not incremental research. It's something that in itself is very exploratory. We don't have like a good definition of what's the right objective function to even measure that a system is doing a good job of unsupervised learning. So of course it's challenging, but at the same time, there's it leaves open a wide field of possibilities, which is what researchers really love. At least that's something that appeals to me.
So today there's so much going on in deep learning, and I think we've passed the point where it's possible for any one human to read every single deep learning paper being published. So I'm curious, what in deep learning today excites you the most?
Well, yes. So I'm very ambitious, and I feel like the current state of the science of deep learning is far from where I'd like it to see it. And I have the impression that our systems right now make mistakes that suggest, the kind of mistakes that suggest that they have a very superficial understanding of the world. So what excites me the most now is a sort of direction of research where we're not trying to build systems that are going to do something useful. We're just going back to principles about how can a computer observe the world, interact with the world, and discover how that world works. Even if that world is simple, something that we can program as a kind of video game, we don't know how to do that well. And that's cool, because I don't have to compete with Google and Facebook and Baidu and so on, right? Because this is a kind of basic research that can be done by anyone in their garage and could change the world. So there are many, of course, many directions to attack this, but I see a lot of the fruitful interactions between ideas in deep learning and reinforcement learning being really important there. I'm really excited that the progress in this direction could have a huge impact on practical applications, actually. Because if you look at some of the big challenges that we have in applications, like how we deal with new domains or categories on which we have too few examples, and in cases where humans are very good at solving those problems, so these transfer learning and generalization issues, they would become much easier to tackle if we had systems that had a better understanding of how the world works, a deeper understanding, right? What is actually going on? What are the causes of what I'm seeing, and how could I, influence what I'm seeing by my actions? So these are the kinds of questions I'm really excited about these days, and I think they connect also the deep learning research that has evolved over the last couple of decades with even older questions in AI, because a lot of the success in deep learning has been with perception. So what's left, right? What's left is sort of higher level cognition, which is about understanding at an abstract level how things work. So our program of understanding higher level abstractions, I think, has not reached those high level of abstractions. And so we have to get there. We have to think about reasoning, about sequential processing of information. We have to think of how causality works and how machines can discover all these things by themselves, potentially guided by humans, but as much as possible in an autonomous way.
And it sounds like from part of what you said that you're a fan of research approaches where you experiment on, I'm going to use the term toy problem, not in a disparaging
Right.
way, but on a small problem, and you're optimistic that that transfers to bigger problems later.
Yes. Yes, yes, and I mean it transfers in a meta way, right? Of course, we're going to have to do some work to scale up and address those problems. But my main motivation for going for those toy problems is that we can understand better our failures, and we can reduce the problem to something we can intuitively sort of manipulate and understand more easily. So sort of a classical divide and conquer, science approach. And also, I think something people don't think about enough is the cycle. The research cycle can be much faster, right? So if I can do an experiment in a few hours, I can progress much faster. If I have to train a huge model that tries to capture the whole common sense and everything in the general knowledge, which will eventually will do. It's just each experiment just takes too much time with current hardware. So while our hardware friends are building machines that are going to be 1,000 or 1,000,000 times faster, I'm doing those toy experiments.
I've also heard you speak about the science of deep learning, not just as an engineering discipline, but doing more work to understand what's really going on. Do you want to share your thoughts on that?
Yeah, absolutely. I fear that a lot of the work that we're doing is sort of like blind people trying to find their way. And you can get a lot of luck and find interesting things that way. But really, if we sort of stop a little bit and try to understand what we're doing in a way that's transferable, because we go down to principles, to theory. But when I say theory, I don't mean necessarily math, right? I'm not like, of course, I like math and so on, but I don't think that we need that everything be formalized mathematically, but be formalized logically, in the sense that I can convince somebody that this should work, or that this makes sense. This is the most important aspect, and then math allows us to make that stronger and tighter. But really, it's more about understanding, and it's about also doing our research not to beat the next baseline or a benchmark, or beat the other guys in the other lab, or the other company. It's more about what kind of question should we ask that will allow us to understand better the phenomena of interest. Like what makes, for example, training in deeper networks harder, or in recurrent nets harder. We have some ideas, but a lot of things we don't understand yet. So we can maybe design experiments whose goal is not to have like a better algorithm, but just to understand better the algorithms we currently have, or what circumstances make a particular algorithm work better, and why. I mean, it's the why that really matters. That's what science is about. It's why.
Right. Today, there are a lot of people that want to enter the field, and I'm sure you've answered this a lot in one-on-one settings. But with all the people watching this on video, what advice would you have for people that want to get into AI, get into deep learning?
Right. So first of all, there are different motivations and different things you could do. What you need to become a deep learning researcher may not be the same as if you want to be an engineer who's going to use deep learning to build products. There's a different level of understanding that's needed in both cases. But in any case, in both cases, practice. So to really master a subject like deep learning, of course, you have to read a lot. You have to practice. So programming the things yourself. Very often, I interview students who have used software, and these days there's so much so good software around that you can just plug and play and understand nothing of what you're doing, or at such a superficial level that then it becomes hard to figure out when it doesn't work, what's going wrong. So actually trying to implement things yourself, even if it's inefficient, but just to make sure you really understand what is going on, is really useful. And trying it yourself.
So that don't just use one of the programming frameworks. You can do everything in a few lines of code, but you don't really know what just happened, right?
Exactly. And I would say even more than that, try to derive the thing yourself from first principles if you can. So that really helps. But yeah, I mean, the usual things you have to do, like reading, looking at other people's code, writing your own code, doing a lot of experiment, making sure you understand everything you do. So, I mean, especially for the science part of it, trying to ask, why am I doing this? Why are people doing this? And maybe the answer is somewhere in the book, and you have to read more. But it's even better if you can actually figure it out by yourself.
Yeah, cool. Yeah, and in fact, of the things to read, you and Ian Goodfellow and Aaron Colville wrote a very highly regarded book.
Thank you, thank you. Yes, it's selling a lot. It's a bit crazy. I feel like there's more people reading this book than people who can read it right now. But yeah, also proceedings of the ICLR iClear conference is probably the best concentrated place of good papers. Of course, there are really good papers at NIPS and ICML and other conferences, but if you really want to go for a lot of good papers, just read the last few ICLR proceedings, and that will give you a really good view of the field.
Cool. Yeah. Any other thoughts when people ask you for advice? How does someone, right, become good at deep learning?
Well, it depends on where you come from. Don't be afraid by the math. Just develop the intuitions, and then the math become really easier to understand once you get the hang of what's going on at an intuitive level. And one good news is that you don't need 5 years of PhD to become proficient at deep learning. You can actually learn pretty quickly. If you have a good background in computer science and math, you can learn enough to use it and build things and start research experiments in just a few months. Something like 6 months for people with the right training. Maybe they don't know anything about machine learning, but if they're good in math and computer science, it can be very fast. And of course, so that means you need to have the right training in math and computer science. Sometimes what you learn in just computer science courses is not enough. You need some continuous path, especially. So this is probability, algebra, and optimization, for example.
I see. And calculus.
And calculus, yeah.
Thanks a lot, Yoshua, for sharing all the comments and insights and advice. Even though I've known you for a long time, there are many details of your early history that I didn't know until now. So thank you.
Well, thank you, Andrew, for doing this special recording and what you're doing. I hope it's going to be used by a lot of people.
Hello, and welcome back. In this week, you learn about optimization algorithms that will enable you to train your neural networks much faster. You've heard me say before that applied machine learning is a highly empirical process. It's a highly iterative process in which you just have to train a lot of models to find one that works really well. So it really helps to be able to train models quickly. One thing that makes that more difficult is that deep learning tends to work best in a regime of big data, when you're able to train your neural networks on a huge data set. And training on a large data set is just slow. So what you find is that having fast optimization algorithms, having good optimization algorithms, can really speed up the efficiency of you and your team. So let's get started by talking about mini-batch gradient descent. You've learned previously that vectorization allows you to efficiently compute on all M examples. That allows you to process your whole training set without an explicit for loop. So that's why we would take our training examples and stack them into this huge matrix, capital X, so x1, x2, x3, and then eventually it goes up to xm if you have M training examples. And similarly for y, this is y1, y2, y3, and so on, up to ym. So the dimension of x was nx by m, and this was 1 by m. Vectorization allows you to process all m examples quickly, relatively quickly. If m is very large, then it can still be slow. So for example, what if m was 5 million? Or 50 million, or even bigger. With the implementation of gradient descent on your whole training set, what you have to do is you have to process your entire training set before you take one little step of gradient descent And then you have to process your entire training sets of 5 million training examples again before you take another little step of gradient descent. So it turns out that you can get a faster algorithm if you let gradient descent start to make some progress even before you finish processing your entire, giant training sets of 5 million examples. In particular, here's what you can do. Let's say that you split up your training set into smaller, little baby training sets. And these baby training sets are called mini batches. And let's say each of your baby training sets have just 1,000 examples each. So you take x1 through x1000, and you call that your first little baby training set, also called a mini batch. And then you take the next 1,000 examples, x1001 through x2000, that's the next 1,000 examples, and call the next one, and so on. And I'm going to introduce a new notation. I'm going to call this x superscript with curly braces 1. And I'm going to call this x superscript with curly braces 2. Now, if you have 5 million training examples total, and each of these little mini batches has 1,000 examples, that means you have 5,000 of these, because 5,000 times 1,000 equals 5 million. So altogether, you would have 5,000 of these mini batches. So it ends with x superscript curly braces 5,000. And then similarly, you do the same thing for y. You'd also split up your training data for y accordingly. So you call that y1, then this is y1001 through y2000. This becomes called y2, and so on, until you have y5000. So now, mini batch number t is going to be comprised of xt and yt, and that is 1,000 training examples with the corresponding input-output pairs. Before moving on, just to make sure our notation is clear, we have previously used superscript round brackets I to index in the training set, so xi is the ith training example. We use superscript square brackets L to index into the different layers of a neural network. So ZL comes from the Z values for the Lth layer of the neural network. And here we're introducing the curly brackets T to index into different mini batches. So you have xt, y, t. And to check your understanding of these, what's the dimension, right, of x, t, and y, t? Well, x is nx by m, so if x1 is 1,000 training examples, or the x values for 1,000 examples, then this dimension should be nx by 1,000, and x2 should also be nx by 1,000, and so on. So all of these should have dimension nx by 1,000, and these should have dimension 1 by 1,000, right? To explain the name of this algorithm, batch gradient descent refers to the gradient descent algorithm we've been talking about previously, where you process your entire training set all at the same time. And the name comes from viewing that as processing your entire batch of training examples all at the same time. I'm not sure it's a great name, but that's just what it's called. Mini batch gradient descent, in contrast, refers to the algorithm, which we'll talk about on the next slide, in which you process a single mini batch xt, yt at the same time, rather than processing your entire training set xy at the same time. So let's see how mini batch gradient descent works. To run mini batch gradient descent on your training sets, you would run for t equals 1 to 5,000, because we had 5,000 mini batches of size 1,000 each. And what you're going to do inside the for loop is basically implement one step of gradient descent using xt, comma, yt. And it's as if you had a training set of size 1,000 examples, and it was as if you were to implement the algorithm you're already familiar with, but just on this little training set size of m equals 1000. Rather than having an explicit for loop over all 1000 examples, you would use vectorization to process all 1000 examples sort of all at the same time. Okay, so let's write this out. First, you implement forward prop on the inputs, so just on xt, and you do that by implementing, z1 equals w1. Now, previously we would just have x there, right? But now you aren't processing the entire training set, you're just processing the first mini batch. So this becomes xt when you're processing mini batch t. And then you would have a1 equals g1 of z1, right? This would be a capital Z, since this is actually a vectorized implementation. And so on until you end up with AL, as I guess GL of ZL, and then this is your prediction. And you notice that here you should use a vectorized implementation. It's just that this vectorized implementation processes 1000 examples at a time rather than 5 million examples. Next, you compute the cost function J, which I'm going to write as 1 over 1000, since here 1000 is the size of your little training set. Sum from I equals 1 through L of really the, loss of y hat I, yi. And this notation for clarity refers to examples from the mini batch xt, yt. And then if you're using regularization, you can also have this regularization term, I guess maybe with a 2 in the denominator, times sum over L. For obedience norm, the weight matrix is squared. So because this is really the cost on just one mini batch, I'm going to index this cost J with a superscript T in curly braces. So you notice that everything we're doing is exactly the same as when we were previously implementing gradient descent, except that instead of doing it on xy, you're now doing it on xt, yt. Next, you'd implement backprop to compute gradients with respect to this jt. So you're still using only xt, yt, and then you update the weights. W, really every WL gets updated as WL minus alpha D WL, and similarly for B. And so this is one pass through your training set using mini batch gradient descent. The code I've written down here is also called doing one epoch of training. An epoch is a word that just means a single pass through the training set. So whereas with batch gradient descent, a single pass through the training set allows you to take only one gradient descent step, with mini batch gradient descent, a single pass through the training set, that is one epoch, allows you to take 5,000 gradient descent steps. Now, of course, if you want to take multiple passes through the training set, which you usually want to, you might want another for loop or another while loop out there. So you keep taking passes through the training set until hopefully you converge or have approximately converged. When you have a large training set, mini batch gradient descent runs much faster than batch gradient descent, and is pretty much what everyone in deep learning will use when you're training on a large data set. In the next video, let's delve deeper into mini batch gradient descent so you can get a better understanding of what it's doing and why it works so well. In the previous video, you saw how you can use mini batch gradient descent to start making progress, to start taking gradient descent steps, even when you're just partway through processing your training set, even for the first time. In this video, you learn more details of how to implement gradient descent and gain a better understanding of what it's doing and why it works. With batch gradient descent, on every iteration you go through the entire training set and you would expect the costs to go down on every single iteration. So if you plot the cost function j as a function of different iterations, it should decrease on every single iteration. And if it ever goes up even on one iteration, then something's wrong. Maybe the learning rate's too big. On mini-batch gradient descent though, if you plot progress on your cost function, then it may not decrease on every iteration. In particular, on every iteration, you're processing some xt, yt, and so if you plot the cost function jt, which is computed using just xt, yt, then it's as if on every iteration you're training on a different training set, or really training on a different mini-batch. So if you plot the cost function j, you're more likely to see something that looks like this. It should trend downwards, but is also going to be a little bit noisier. So if you plot j of t as you're training mini-batch gradient descent and maybe over multiple epochs, you might expect to see a curve like this. So it's okay if it doesn't go down on every iteration, but it should trend downwards. And the reason it'll be a little bit noisy is that maybe x1, y1 is just a relatively easy mini-batch, so your cost might be a bit lower, but then maybe just by chance, x2, y2 is just a harder mini-batch, maybe even some mislabeled examples in it, in which case the cost would be a bit higher, and so on. So that's why you get these oscillations as you plot the cost when you're running mini-batch gradient descent. Now, one of the parameters you need to choose is the size of your mini-batch. So m was the training set size. On one extreme, if the mini-batch size is equal to m, then you just end up with batch gradient descent. Right, so in this extreme, you would just have one mini batch, x1, y1, and this mini batch is equal to your entire training set. So setting the mini batch size to m just gives you batch gradient descent. The other extreme would be if your mini batch size were equal to 1. This gives you an algorithm called stochastic gradient descent. And here, every example is its own mini batch. So what you do in this case is you look at the first mini batch, so x1, y1, but when your mini batch size is 1, this just has your first training example, and you take a gradient descent step with your first training example. And then you next take a look at your second mini batch, which is just your second training example, and take a gradient descent step with that. And then you do it with the third training example and so on, looking at just one single training example at a time. So let's look at what these two extremes will do on optimizing this cost function. If these are the contours of a cost function you're trying to minimize, so your minimum is there, then batch gradient descent might start somewhere and be able to take relatively low noise, relatively large steps, and just keep marching to the minimum. In contrast, with stochastic gradient descent, if you start somewhere, let's pick a different starting point, then on every iteration, you're taking gradient descent with just a single training example. So most of the time you hit toward the global minimum, but sometimes you hit in the wrong direction if that one example happens to point you in a bad direction. So stochastic gradient descent can be extremely noisy, and on average it'll take you in a good direction, but sometimes it'll head in the wrong direction as well. And stochastic gradient descent won't ever converge. You'll always just kind of oscillate and wander around the region of the minimum, but it won't ever just head to the minimum and stay there. In practice, the mini batch size you use will be somewhere in between. Somewhere between in 1 and m. And 1 and m are respectively too small and too large. And here's why. If you use batch gradient descent, so this is your mini batch size equals m, then you're processing a huge training set on every iteration. So the main disadvantage of this is that it takes too much time, too long per iteration, assuming you have a very large training set. If you have a small training set, then batch gradient descent is fine. If you go to the opposite, if you use stochastic gradient descent, then it's nice that you get to make progress after processing just one example. That's actually not a problem. And the noisiness can be ameliorated or can be reduced by just using a smaller learning rate. But the huge disadvantage of stochastic gradient descent is that you lose almost all your speed up from vectorization. Because here, you're processing a single training example at a time, the way you process each example is going to be very inefficient. So what works best in practice is something in between, where you have some, mini batch size that's not too big or too small. And this gives you, in practice, the fastest learning. And you notice that this has two good things going for it. One is that you do get a lot of vectorization. So in the example we used on the previous video, if your mini batch size was 1,000 examples, then you might be able to vectorize across 1,000 examples, which is going to be much faster than processing the examples one at a time. And second, you can also make progress without needing to wait till you process the entire training set. So again, using the numbers we had from the previous video, each epoch or each pass to your training set allows you to take 5,000 gradient descent steps. So in practice, there'll be some in-between mini batch size that works best. And so with mini batch gradient descent, if you start here, maybe one iteration does this, two iterations, 3, 4, and it's not guaranteed to always head toward the minimum, but it tends to head more consistently in the direction of the minimum than stochastic gradient descent. And then it doesn't always exactly converge. It'll oscillate in a very small region. If that's an issue, you can always reduce the learning rate slowly. We'll talk more about learning rate decay or how to reduce the learning rate in a later video. So if the mini batch size should not be m and should not be 1, but it should be something in between, how do you go about choosing it? Well, here are some guidelines. First, if you have a small training set, just use batch gradient descent. If you have a small training set, then no point using mini batch gradient descent. You can process the whole training set quite fast, so you might as well use batch gradient descent. What does small training set mean? I would say, if it's less than maybe 2,000, it'd be perfectly fine to just use batch gradient descent. Otherwise, if you have a bigger training set, typical mini batch sizes would be anything from 64 up to maybe 512 are quite typical. And because of the way computer memory is laid out and accessed, sometimes your code runs faster if your mini batch size is a power of 2. Right? So 64 is 2 to the 6 is 2 to the 7, 2 to the 8, 2 to the 9. So often I'll implement my mini batch size to be a power of 2. I know that in the previous video, I used a mini batch size of 1,000. If you really wanted to do that, I would recommend you just use 1,024, which is to the power of 10. And you do see mini batch sizes of size 1024. It is a bit more rare. This range of mini batch size is a little bit more common. One last tip is to make sure that your mini batch, all of your xt, yt, that fits in CPU, GPU memory. And this really depends on your application and how large a single training example is. But if you ever process a mini batch that doesn't actually fit in CPU, GPU memory, whatever you're using to process the data, then you find that the performance suddenly falls off a cliff and is suddenly much worse. So I hope this gives you a sense of the typical range of mini batch sizes that people use. In practice, of course, the mini batch size is actually another hyperparameter that you might do a quick search over to try to figure out which one is most efficient at reducing your cost function j. So what I would do is just try several different values, try a few different powers of 2, and then see if you could pick one that makes your gradient descent optimization algorithm as efficient as possible. But hopefully this gives you a set of guidelines for how to get started with that hyperparameter search. You now know how to implement mini batch gradient descent and make your algorithm run much faster, especially when you're training on a large training set. But it turns out there are even more efficient algorithms than gradient descent or mini batch gradient descent. Let's start talking about them in the next few videos. I want to show you a few optimization algorithms that are faster than gradient descent. In order to understand those algorithms, you need to be able to use something called exponentially weighted averages, also called exponentially weighted moving averages in statistics. Let's first talk about that, and then we'll use this to build up to more sophisticated optimization algorithms. So even though I now live in the United States, I was born in London. So for this example, I got the daily temperature from London from last year. So on January 1st, temperature was 40 degrees Fahrenheit. And I know most of the world uses a Celsius system, but I guess I live in the United States, which uses Fahrenheit. So that's 4 degrees Celsius. And on January 2nd, it was 9 degrees Celsius and so on. And then about halfway through the year, a year has 365 days. So this would be sometime, day number 180 would be sometime in late May, I guess. It was 60 degrees Fahrenheit, which is 15 degrees Celsius, and so on. So it started to get warmer towards summer, and it was colder in January. So if you plot the data, you end up with this, with day 1 being sometime in January, that being the beginning of summer, and that's the end of the year, kind of late December. So this would be January. January 1st is the middle of the year, approaching summer, and this would be the data from the end of the year. So this data looks a little bit noisy, and if you want to compute the trends, kind of the local average or moving average of the temperature, here's what you can do. Let's initialize V0 equals 0, and then on every day, we're going to average it with a weight of 0.9 times whatever was the previous value plus 0.1 times that day's temperature. So theta 1 here would be the temperature from this first day. And on the second day, we're again going to take a weighted average, so 0.9 times the previous value plus 0.1 times today's temperature, and so on. V2 plus 0.1 times theta 3, and so on. And the more general formula is V on a given day is 0.9 times V from the previous day plus 0.1 times the temperature of that day. So if you compute this and plot it in red, this is what you get. You get a moving average, or what's called an exponentially weighted average of the daily temperature. So let's look at the equation we had from the previous slide. It was Vt equals, previously we had 0.9, we're going to turn that into parameter beta. Beta times Vt minus 1 plus, and then previously we had 0.1, we're going to turn that into 1 minus beta times theta t. So previously we had beta equals 0.9. It turns out that for reasons we'll go into later, when you compute this, you can think of Vt as approximately averaging over something like 1 over 1 minus beta days temperature. So for example, when beta equals 0.9, you could think of this as averaging over the last 10 days temperature. And that was the red line. Now let's try something else. Let's set beta to be very close to 1. Let's say it's 0.98. Then if you look at 1 over 1 minus 0.98 this is equal to 50. So this is, think of this as averaging over roughly the last 50 days temperature. And if you plot that, you get this green line. So notice a couple things. With this very high value of beta, the plot you get is much smoother because you're now averaging over more days of temperature. So the curve is just less wiggly, is now smoother. But on the flip side, the curve is now shifted further to the right because you're now averaging over a much larger window of temperatures. And by averaging over a larger window, this formula, this exponentially weighted average formula, it adapts more slowly when the temperature changes. Right, so there's just a bit more latency. And the reason for that is when beta is equal to 0.98, then it's giving a lot of weight to the previous value and a much smaller weight, just 0.02, to whatever you're seeing right now. So when the temperature changes, when temperature goes up or down, this exponentially weighted average just adapts more slowly when beta is so large. Now let's try another value. If you set beta to another extreme, let's say it is 0.5, then this, by the formula we have on the right, this is something like averaging over just 2 days temperature. And you plot that, you get this yellow line. And by averaging only over 2 days temperature, you have it's as if you're averaging over a much shorter window. So you're much more noisy, much more susceptible to outliers. But this adapts much more quickly to if the temperature changes. So this formula is how you implement an exponentially weighted average. Again, it's called an exponentially weighted moving average in the statistics literature, and I'm going to call it exponentially weighted average for short. And by varying this parameter, or later we'll see it's actually a hyperparameter of your learning algorithm, you can get slightly different effects, and there will usually be some value in between that works best. That gives you the red curve, which maybe looks like a better average of the temperature than either the green or the yellow curve. You now know the basics of how to compute exponentially weighted averages. In the next video, let's gain a bit more intuition about what it's doing. In the last video, we talked about exponentially weighted averages. This will turn out to be a key component of several optimization algorithms that you use to train your neural networks. So in this video, I want to delve a little bit deeper into intuitions for what this algorithm is really doing. Recall that this is the key equation for implementing exponentially weighted averages. And so if beta equals 0.9, you got the red line. If it was much closer to 1, if it was 0.98, you get the green line. And if it's much smaller, maybe 0.5, you get the yellow line. Let's look at a bit more at the math to understand how this is computing averages of the daily temperature. So here's that equation again, and let's set beta equals 0.9 and write out a few equations that this corresponds to. So whereas when implementing it, you'd have t going from 0 to 1 to 2 to 3 increasing values of t. To analyze it, I've written it with decreasing values of t, right? And this goes on. So let's take this first equation here and understand what V100 really is. So V100 is going to be let me reverse these two terms. This is going to be 0.1 times theta 100 plus 0.9 times whatever the value was on the previous day. Now, but what is V99? Well, we can just plug it in from this equation. So this is just going to be 0.1 times theta 99. And again, I've reversed these two terms, right? Plus 0.9 times V98. But then what is V98? Well, you can just get that from here. So you can just plug in here 0.1 times theta 98 plus 0.9 times V97, and so on. And if you multiply all of these terms out, you can show that V100 is 0.1 times theta 100 plus, now let's look at coefficient on theta 99. It's going to be 0.1 times 0.9 times theta 99. Now let's look at the coefficient on theta 98. There's a 0.1 here times 0.9 times 0.9. So if you expand out the algebra, this becomes 0.1 times 0.9 squared times theta 98. And if you keep expanding this out, you find that this becomes 0.1 times 0.9 cubed theta 97 plus 0.1 times 0.9 to the fourth times theta 96 plus ... So this is really a weighted sum, and thus a weighted average of theta 100, which is the current day's temperature. If we're looking from a perspective of V100, which you calculate on the 100th day of the year. But so is a sum of, theta 100, theta 99, theta 98, theta 97, theta 96, and so on. So one way to draw this in pictures would be if, let's say we have some number of days of temperature. So this is theta and this is t, right? So theta 100 would be some value, then theta 99 would be some value, theta 98. So these are, so this is t equals 100, 99, 98, and so on, right? So you have some number of days of temperature. And what we have is then an exponentially decaying function. So starting from 0.1 to 0.9 times 0.1 to 0.9 squared times 0.1 to, and so on. So you have this exponentially decaying function. And the way you compute V100 is you take the element-wise product between these two functions and sum it up. So you take this value, theta 100 times 0.1, times this value, theta 99 times 0.1 times 0.9, that's the second term, and so on. So it's really taking the daily temperature, multiplying with this exponentially decaying function, and then summing it up. And this becomes your V100. It turns out that up to details I'll talk about later, but all of these coefficients add up to 1, or add up to very close to 1, up to a detail called bias correction, which we'll talk about in the next video. But because of that, this really is an exponentially weighted average. And finally, you might wonder, how many days temperature is this averaging over? Well, it turns out that 0.9, right, to the power of 10 is about 0.35. And this turns out to be about 1 over e, 1 over the base of natural logarithms. And more generally, if you have 1 minus epsilon, so in this example, epsilon would be 0.1. So if this was 0.9, then 1 minus epsilon to the 1 over epsilon, this is about 1 over e. This is about 0.34, 0.35. And so, in other words, it takes about 10 days for the height of this to decay to, around 1/3, or really 1 over e of the peak. So it's because of this that when beta equals 0.9, we say that it takes, this is as if you're computing an exponentially weighted average that focuses on just the last 10 days temperature, because it's after 10 days that the weight decays to, less than about 1/3 of the weight of the current day. Whereas in contrast, if beta was equal to 0.98, then, well, what do you need 0.98 to the power of in order for this to be really small? It turns out that 0.98 to the power of 50 will be approximately equal to 1 over e. So the weight will be pretty big. It'll be bigger than 1 over e for the first 50 days, and then it'll decay quite rapidly over that. So intuitively, this is a hard and fast thing. You can think of this as averaging over about 50 days temperature, because in this example, to use the notation here on the left, is as if epsilon is equal to 0.02, so 1 over epsilon is 50. And this, by the way, is how we got the formula that we're averaging over 1 over 1 minus beta or so days. Right here, epsilon really plays the role of 1 minus beta. It tells you up to some constant roughly how many days temperature you should think of this as averaging over. But this is just a rule of thumb for how to think about it, and isn't a formal mathematical statement. Finally, let's talk about how you actually implement this. Recall that we start off with V0, initialize as 0, then you compute V1 on the first day, V2, and so on. Now, to explain the algorithm, it was useful to write down V0, V1, V2, and so on as distinct variables. But if you're implementing this in practice, this is what you do. You initialize V to be equal to 0, and then on day 1, you would set V equals beta times V plus 1 minus beta times theta 1. And then on the next day, you would update V to be equal to beta V plus 1 minus beta theta 2, and so on. And I'm sometimes going to use this notation, V subscript theta, to denote that V is computing this exponentially weighted average of the parameter theta. So just to say this again, but in for loop format, you set v theta equals 0, and then repeatedly, kind of on each day, you would get next theta t, and then set v theta gets updated as beta times the old value of v theta plus 1 minus beta, times the current value of v theta. So one of the advantages of this exponentially weighted average formula is that it takes very little memory. You just need to keep, this one row number in computer memory, and you keep on overwriting it with this formula based on the latest value that you got. And it's really this reason, the efficiency, it just takes, one line of code basically, and just storage and memory for a single row number to compute this exponentially weighted average is really not the best way, not the most accurate way to compute an average. If you were to compute a moving window where you explicitly sum over the last 10 days, the last 50 days temperature and just divide by 10 or divide by 50, that usually gives you a better estimate. But the disadvantage of that, of explicitly keeping all the temperatures around and summing of the last 10 days, is it requires more memory and it's just more complicated to implement and it's computationally more expensive. So for things, and we'll see some examples in the next few videos, where you need to compute averages of a lot of variables, this is a very efficient way to do so, both from a computation and memory efficiency point of view, which is why it's used a lot in machine learning. Not to mention that it's just one line of code, which is maybe another advantage. So now you know how to implement exponentially weighted averages. There's one more technical detail that's worth you knowing about called bias correction. Let's see that in the next video. And then after that, you'll be able to use this to build a better optimization algorithm than the straightforward gradient descent. You've learned how to implement exponentially weighted averages. There's one technical detail called bias correction that can make your computation of these averages more accurately. Let's see how that works. In the previous video, you saw this figure for beta equals 0.9, this figure for beta equals 0.98. But it turns out that if you implement the formula as written here, you won't actually get the green curve when, say, beta equals 0.98. You actually get the purple curve here. And you notice that the purple curve starts off really low. So let's see how to fix that. When you're implementing a moving average, you initialize it with v0 equals 0, and then v1 is equal to 0.98 v0 plus 0.02 theta 1. But v0 is equal to 0, so that term just goes away. So v1 is just 0.02 times theta 1. So that's why if the first day's temperature is, say, 40 degrees Fahrenheit, then v1 will be 0.02 times 40, which is 8. So you get a much lower value down here. So it's not a very good estimate of the first day's temperature. v2 will be 0.98 times v1 plus 0.02 times theta 2. And if you plug in v1, which is this, down here, and multiply it out, then you find that v2 is actually equal to 0.98 times 0.02 times theta 1 plus 0.02 times theta 2, and that's 0.0196 theta 1 plus 0.02 theta 2. So again, assuming theta 1 and theta 2 are positive numbers, when you compute this, v2 will be much less than theta 1 or theta 2. So v2 isn't a very good estimate of the first 2 days' temperature of the year. So it turns out that there's a way to modify this estimate that makes it much better, or that makes it more accurate, especially during this initial phase of your estimate, which is that instead of taking vt, take vt divided by 1 minus beta to the power of t, where t is the current day that you're on. So let's take a concrete example. When t is equal to 2, 1 minus beta to the power of t is 1 minus 0.98 squared. And it turns out that this is 0.0396. And so your estimate of the temperature on day 2 becomes v2 divided by 0.0396. And this is going to be 0.0196 times theta 1 plus 0.02 theta 2. You notice that these two things adds up to the denominator, 0.0396 0.96, and so this becomes a weighted average of theta 1 and theta 2, and this removes this bias. So you notice that as t becomes large, beta to the t will approach 0, which is why when t is large enough, the bias correction makes almost no difference. This is why when t is large, the purple line and the green line, pretty much overlap. But during this initial phase of learning, when you're still warming up your estimates, when bias correction can help you to obtain a better estimate of the temperature. And it's this bias correction that helps you go from the purple line to the green line. So in machine learning, for most implementations of the exponentially weighted average, people don't often bother to implement bias correction because most people would rather just wait that initial period and have a slightly more biased estimate and then go from there. But if you are concerned about the bias during this initial phase while your exponentially weighted moving average is still warming up, then bias correction can help you get a better estimate early on. So with that, you now know how to implement exponentially weighted moving averages. Let's go on and use this to build some better optimization algorithms. There's an algorithm called momentum, or gradient descent with momentum, that almost always works faster than the standard gradient descent algorithm. In one sentence, the basic idea is to compute an exponentially weighted average of your gradients, and then to use that gradient to update your weights instead. In this video, let's unpack that one sentence description and see how you can actually implement this. As the most of an example, let's say that you're trying to optimize a cost function which has contours like this. So the red dot denotes the position of the minimum. Maybe you start gradient descent here, and if you take one iteration of gradient descent, either batch or mini batch gradient descent, maybe you end up heading there. But now you're on the other side of this ellipse. You and if you take another step of gradient descent, maybe you end up doing that. And then another step, and so on. And you see that gradient descents will, sort of take a lot of steps, right? And just slowly oscillate toward the minimum. And these up and down oscillations slows down gradient descent and prevents you from using a much larger learning rate. In particular, if you were to use a much larger learning rate, you might end up overshooting and end up diverging like so. And so the need to prevent the oscillations from getting too big forces you to use a learning rate that's not itself too large. Another way of viewing this problem is that on the vertical axis, you want your learning to be a bit slower because you don't want those oscillations. But on the horizontal axis, you want faster learning, right? Because you want it to aggressively move from left to right toward that minimum, toward that red dot. So here's what you can do if you implement gradient descent with momentum. On each iteration, or more specifically, during iteration t, you would compute the usual derivatives dw, db. I'll omit the superscript square bracket else, but you compute dw, db on the current mini batch. And if you're using batch gradient descent, then the current mini batch would be just your whole batch. And this works as well for batch gradient descent. So if your current mini batch is your entire training set, this works fine as well. And then what you do is you compute v dw to be beta vdw plus 1 minus beta dw. So this is similar to when we were previously computing v theta equals beta v theta plus 1 minus beta theta t, right? So it's computing moving average of the derivatives for w you're getting. And then you similarly compute vdb equals that plus 1 minus beta times db. And then you would update your weights using w gets updated as w minus the learning rate times, instead of updating it with dw, with the derivative, you would update it with v dw. And similarly, b gets updated as b minus alpha times v db. So what this does is smooth out the steps of gradient descent. For example, let's say that the last few derivatives you computed were this this, this. If you average out these gradients, you find that the oscillations in the vertical direction will tend to average out to something closer to 0. So in the vertical direction, where you want to slow things down, this will average out positive and negative numbers, so the average should be closer to 0. Whereas on the horizontal direction, all the derivatives are pointing to the right in the horizontal direction, so the average in the horizontal direction will still be pretty big. So that's why with this algorithm, with a few iterations, you find that the gradient descent with momentum ends up eventually just taking steps that are much smaller oscillations in the vertical direction, but are more directed toward the horizontal, to just moving quickly in the horizontal direction. And so this allows your algorithm to take a more straightforward path, or less, to damp out the oscillations in its path to the minimum. One intuition for this momentum, which works for some people, not for everyone, is that if you're trying to minimize a bow-shaped function, right? This is really the contours of a bow. I guess I'm not very good at drawing. But if you're trying to minimize this type of bow-shaped function, then these derivative terms you can think of as providing acceleration to a ball that you're rolling downhill, and these momentum terms you can think of as representing the velocity. And so imagine that you have a bow and you take a ball, and the derivative imparts acceleration to this little ball. It's a little ball that's rolling down this hill, right? And so it rolls faster and faster because of acceleration. And beta, because this is a number a little bit less than 1, displays a rho of friction, and it prevents your ball from speeding up without limit. But so rather than gradient descent just taking every single step independently of all previous steps, now your little ball can roll downhill and gain momentum, but it can accelerate down this bow and therefore gain momentum. I find that this ball rolling down a bow analogy, it seems to work for some people who enjoy physics intuitions, but it doesn't work for everyone. So if this analogy of a ball rolling down a bow doesn't work for you, don't worry about it. Finally, let's look at some details on how you implement this. Here's the algorithm, and so you now have two hyperparameters, the learning rate alpha as well as this parameter beta, which controls your exponentially weighted average. The most common value for beta is 0.9. We're averaging over the last 10 days temperature, so this is like averaging over the last 10 iterations gradient. And in practice, beta equals 0.9 works very well. Feel free to try different values and do some hyperparameter search, but 0.9 appears to be a pretty robust value. Well, and how about bias correction, right? So do you want to take VDW and VDB and divide it by 1 minus beta to the t? In practice, people don't usually do this because after just 10 iterations, your moving average will have warmed up and there's no longer a bias estimate. So in practice, I don't really see people bothering with bias correction when implementing gradient descent with momentum. And of course, this process is initialized with VDW equals 0. Note that this is a matrix of zeros with the same dimension as DW, which is the same dimension as W, and VDB is also initialized to a vector of 0, so the same dimension as DB, which in turn has the same dimension as B. Finally, I just mentioned that if you read the literature on gradient descent with momentum, often you see it with this term omitted, with this 1 minus beta term omitted. So you end up with VDW equals beta VDW plus DW. And the net effect of using this version in purple is that VDW ends up being scaled by a factor of 1 minus beta, or really 1 over 1 minus beta. And so when you're performing these gradient descent updates, alpha just needs to change by a corresponding value of or 1 over 1 minus beta. In practice, both of these will work just fine. It just affects what's the best value of the learning rate alpha. But I find that this particular formulation is a little less intuitive, because one impact of this is that if you end up tuning the hyperparameter beta, then this affects the scaling of VDW and VDB as well, and so you end up needing to retune the learning rate alpha as well, maybe. So I personally prefer the formulation that I had written here on the left rather than leaving out the 1 minus beta term. But so I tend to use the formula on the left, the printed formula with the 1 minus beta term. But both versions having beta equals 0.9 is a common choice of hyperparameter. It's just that alpha, the learning rate, will need to be tuned differently for these two different versions. So that's it for gradient descent with momentum. This will almost always work better than the straightforward gradient descent algorithm without momentum. But there's still other things we could do to speed up your learning algorithm. Let's continue talking about these in the next couple videos. You've seen how using momentum can speed up gradient descent. There's another algorithm called RMSprop, which stands for root mean square prop. They can also speed up gradient descent. Let's see how it works. Recall our example from before that if you implement gradient descent, you can end up with huge oscillations in the vertical direction, even whilst trying to make progress in the horizontal direction. In order to provide intuition for this example, let's say that the vertical axis is the parameter b and the horizontal axis is the parameter w. Right? It really could be w1 and w2 or some of the standard parameters, but this is named as b and w for the sake of intuition. And so you want to slow down the learning in the b direction or in the vertical direction and speed up learning, or at least not slow it down, in the horizontal direction. So this is what the RMSprop algorithm does to accomplish this. On iteration t, it will compute, as usual, the derivatives dw, db on the current mini batch. So I was going to keep this exponentially weighted average. Instead of VDW, I'm going to use new notation SDW. So SDW is equal to beta times their previous value plus 1 minus beta times DW squared. I sometimes write this DW star star 2 to denote the exponentiation. Let's just write this as DW squared. So for clarity, this squaring operation is an element-wise squaring operation. So what this is doing is really keeping an exponentially weighted average of the squares of the derivatives. And similarly, we also have SDB equals beta SDB plus 1 minus beta dB squared. And again, the squaring is an element-wise operation. Next, RMSprop then updates the parameters as follows. W gets updated as W minus the learning rate. And whereas previously we had alpha times dw, now is dw divided by square root of s dw. And b gets updated as b minus the learning rate times, instead of just the gradient, this is also divided by, now divided by s db. So let's gain some intuition about how this works. Recall that in the horizontal direction, or in this example, in the W direction, we want learning to go pretty fast, whereas in the vertical direction, or in this example, in the B direction, we want to slow down or to damp out the oscillations in the vertical direction. So with these terms, SDW and SDB, what we're hoping is that SDW will be relatively small, so that here we're dividing by a relatively small number, whereas SDB would be relatively large, so that here we're dividing by a relatively large number in order to slow down the updates in the vertical direction. And indeed, if you look at the derivatives, these derivatives are much larger in the vertical direction than in the horizontal direction. So, the slope is very large in the B direction, right? So with derivatives like this, this is a very large dB and a relatively small dW. Because the function is sloped much more steeply in the vertical direction, that is in the B direction, than in the W direction, than in the horizontal direction. And so dB squared will be relatively large, so SDB will be relatively large, whereas compared to that, dW will be smaller, or dW squared will be smaller, and so SDW will be smaller. So the net effect of this is that your updates in the vertical direction are divided by a much larger number, and so that helps damp out the oscillations, whereas the updates in the horizontal direction are divided by a smaller number. So the net impact of using RMSprop is that your updates will end up looking more like this. right? That your updates in the vertical direction get damped out, but in horizontal direction, it can keep going. And one effect of this is also that you could therefore use a larger learning rate alpha and get faster learning without it diverging in the vertical direction. Now, just for the sake of clarity, I've been calling the vertical and horizontal directions B and W just to illustrate this. In practice, you're in a very high dimensional space of parameters, so maybe the vertical dimensions where you're trying to dampen oscillations is some set of parameters, W1, W2, W17, and the horizontal dimensions might be W3, W4, and so on, right? And so the separation is a W and B is just for illustration. In practice, dW is a very high dimensional parameter vector. dB is also a very high dimensional parameter vector. But the intuition is that in dimensions where you're getting these oscillations, you end up computing a larger sum or weighted average for these squares of derivatives, and so you end up damping out the directions in which there are these oscillations. So that's RMSprop, and it stands for root mean squared, because root mean squared prop, because here you're squaring the derivatives and then you take the square root here at the end. So finally, just a couple last details on this algorithm before we move on. In the next video, we're actually going to combine RMSprop together with momentum. So rather than using the hyperparameter beta, which we had used for momentum, I'm going to call this hyperparameter beta 2, just to not clash, the same hyperparameter for both momentum and for RMSprop. And also to make sure that your algorithm doesn't divide by 0. What if square root of SDW, right, is very close to 0? Then this thing could blow up. Just to ensure numerical stability, when you implement this in practice, you add a very, very small epsilon to the denominator. Doesn't really matter what epsilon is. You use 10 to the negative 8 would be a reasonable default, but this just ensures slightly greater numerical stability that, for numerical round-off for whatever reason, that you don't end up dividing by a very small number. So that's RMSprop, and similar to momentum, has the effect of damping out the oscillations in gradient descent, in mini-batch gradient descent, and allowing you to maybe use a larger learning rate alpha, and certainly speeding up the learning speed of your algorithm. So now you know how to implement RMSprop, and this will be another way for you to speed up your learning algorithm. One fun fact about RMSprop, it was actually first proposed not in an academic research paper, but in a Coursera course that Jeff Hinton had taught on Coursera many years ago. I guess Coursera wasn't intended to be a platform for dissemination of novel academic research, but it worked out pretty well in that case. It was really from the Coursera course that RMSprop started to become widely known and then really took off. We've talked about momentum, we've talked about RMSprop. It turns out that if you put them together, you can get an even better optimization algorithm. Let's talk about that in the next video. During the history of deep learning, many researchers, including some very well-known researchers, sometimes propose optimization algorithms and show they work well in a few problems, but those optimization algorithms subsequently were shown not to really generalize that well to the wide range of neural networks you might want to train. So over time, I think the deep learning community actually developed some amount of skepticism about new optimization algorithms, and a lot of people felt that gradient descent with momentum really works well. It was difficult to propose things that work much better. So RMSprop and the Adam optimization algorithm, which we'll talk about in this video, is one of those rare algorithms that has really stood up and has been shown to work well across a wide range of deep learning architectures. So this is one of the algorithms that I wouldn't hesitate to recommend you try, because many people have tried it and seen it work well on many problems. And the Adam optimization algorithm is basically taking momentum and RMSprop and putting them together. So let's see how that works. To implement Adam, you would initialize VDW equals 0, SDW equals 0, and similarly VDB, SDB equals 0. And then on iteration T, you would compute the derivatives, compute DW, DB using current mini-batch. So usually you do this with mini-batch gradient descent. And then you do the momentum exponentially weighted average. So VDW equals beta, but now I'm going to call this beta 1 to distinguish it from the hyperparameter beta 2 we'll use for the RMSprop portion of this. So this is exactly what we had when we're implementing momentum, except that I've now called the hyperparameter beta 1 instead of beta. And similarly, you'd have VDB as follows. So 1 minus beta 1 times dB. And then you do the RMSprop like update as well. So now you have a different hyperparameter beta 2 plus 1 minus beta 2 dW squared. And again, the squaring there is element-wise squaring of your derivatives dW. And then SdB is equal to this plus 1 minus beta 2 times dB. So this is the momentum-like update with hyperparameter beta 1, and this is the RMSprop-like update with hyperparameter beta 2. In the typical implementation of ADAM, you do implement bias correction. So you're going to have V corrected. Corrected means after bias correction. dW equals V dW divided by 1 minus beta 1 to the power of t, if you've done t iterations, and similarly V dB corrected equals V dB divided by 1 minus beta 1 to the power of t. And then similarly, you implement this bias correction on S as well. So that's S dW divided by 1 minus beta 2 to the t, and S dB corrected equals S dB divided by 1 minus beta 2 to the t. Finally, you perform the update. So W gets updated as W minus alpha times. So if we're just implementing momentum, you'd use V dW, or maybe V dW corrected. But now we add in the RMSprop portion of this, so we're also going to divide by square root of S dW corrected plus epsilon. And similarly, B gets updated as a similar formula. V dB corrected divided by square root S corrected dB plus epsilon. And so this algorithm combines the effect of gradient descent with momentum together with gradient descent with RMSprop. And this is commonly used learning algorithm that's proven to be very effective for many different neural networks of a very wide variety of architectures. So this algorithm has a number of hyperparameters. The learning rate hyperparameter alpha is still important and usually needs to be tuned. So you just have to try a range of values and see what works. A common choice, really the default choice for beta 1 is 0.9. So this is the moving average, weighted average of dW, right? This is the momentum-like term. The hyperparameter for beta 2, the authors of the ADAM paper, inventors of the ADAM algorithm, recommend 0.999. Again, this is computing the moving weighted average of dW squared as well as dB squared. And then epsilon, the choice of epsilon doesn't matter very much, but the authors of the ADAM paper recommended 10 to the minus 8, but this parameter, you really don't need to set it, and it doesn't affect performance much at all. But when implementing ADAM, what people usually do is just use the default values of beta 1 and beta 2, as well as epsilon. I don't think anyone ever really tunes epsilon. And then try a range of values of alpha to see what works best. You could also tune beta 1 and beta 2, but it's not done that often among the practitioners I know. So where does the term ADAM come from? ADAM stands for Adaptive Moment Estimation. So beta 1 is computing the mean of the derivatives. This is called the first moment, and beta 2 is used to compute exponentially weighted average of the squares, and that's called the second moment. So that gives rise to the name adaptive moment estimation, but everyone just calls it the ADAM optimization algorithm. And by the way, one of my long-term friends and collaborators is called Adam Coates far as I know, this algorithm doesn't have anything to do with him, except for the fact that I think he uses it sometimes. But sometimes I get asked that question, so just in case you're wondering. So that's it for the Adam optimization algorithm. With it, I think you'll be able to train your neural networks much more quickly. But before we wrap up for this week, let's keep talking about hyperparameter tuning, as well as gain some more intuitions about what the optimization problem for neural networks looks like. In the next video, we'll talk about learning rate decay. One of the things that might help speed up your learning algorithm is to slowly reduce your learning rate over time. We call this learning rate decay. Let's see how you can implement this. Let's start with an example of why you might want to implement learning rate decay. Suppose you're implementing mini-batch gradient descent with a reasonably small mini-batch. Maybe your mini-batch has just 64, 128 examples. Then as you iterate, your steps will be a little bit noisy and it will tend toward this minimum over here, but it won't exactly converge. But your algorithm might just end up wandering around and never really converge because you're using some fixed value for alpha and there's just some noise in your different mini batches. But if you were to slowly reduce your learning rate alpha, then during the initial phases, while your learning rate alpha is still large, you can still have relatively fast learning. But then as alpha gets smaller, your steps you take will be slower and smaller. And so you end up oscillating in a tighter region around this minimum rather than wandering far away even as training goes on and on. So the intuition behind slowly reducing alpha is that maybe during the initial steps of learning, you could afford to take much bigger steps, but then as learning approaches convergence, then having a slower learning rate allows you to take smaller steps. So here's how you can implement learning rate decay. Recall that one epoch is one pass through the data, right? So if you have a training set as follows, maybe break it up into different mini batches. Then the first pass through the training set is called the first epoch, and then the second pass is the second epoch, and so on. So one thing you could do is set your learning rate alpha to be equal to 1 over 1 plus a parameter which I'm going to call the decay rate times the epoch num. And this is going to be times some initial learning rate alpha 0. Note that the decay rate here becomes another hyperparameter which you might need to tune. So here's a concrete example. If you take several epochs, so several passes through your data, if alpha 0 is equal to 0.2 and the decay rate is equal to 1, then during your first epoch, alpha will be 1 over 1 plus 1 times alpha 0, so your learning rate will be 0.1. That's just evaluating this formula when the decay rate is equal to 1 and the epoch num is 1. On the second epoch, your learning rate decays to 0.67, on the third 0.5, on the fourth 0.4, and so on. And feel free to evaluate more of these values yourself and get a sense that as a function of your epoch number, your learning rate gradually decreases, right? As this, according to this formula up on top. So if you wish to use learning rate decay, what you can do is try a variety of values of both hyperparameter alpha 0 as well as of this decay rate hyperparameter, and then try to find a value that works well. Other than this formula for learning rate decay, there are a few other ways that people use. For example, this is called exponential decay, where alpha is equal to some number less than 1, such as 0.95 times epoch num times alpha 0. So this will exponentially quickly decay your learning rate. Other formulas that people use are things like alpha equals some constant over epoch num square root times alpha 0, or some constant k, another hyperparameter, over the mini batch number t square rooted times alpha 0. And sometimes you also see people use a learning rate that decreases in discrete steps, where for some number of steps you have some learning rate, and then after a while you decrease it by 1/2, after a while by 1/2, after a while by 1/2. And so this is a discrete staircase. So far we've talked about using some formula to govern how alpha, the learning rate, changes over time. One other thing that people sometimes do is manual decay. And so if you're training just one model at a time, and if your model takes many hours or even many days to train, what some people will do is just wash your model as it's training over a large number of days, and then manually say, oh, it looks like the learning rate slowed down. I'm going to decrease alpha a little bit. Of course, this works. This manually controlling alpha, really tuning alpha by hand, hour by hour, day by day. This works only if you're training only a small number of models, but sometimes people do that as well. So now you have a few more options for how to control the learning rate alpha. Now, in case you're thinking, wow, this is a lot of hyperparameters, how do I select amongst all these different options? I would say don't worry about it for now. In next week, we'll talk more about how to systematically choose hyperparameters. For me, I would say that learning rate decay is usually lower down on the list of things I try. Setting alpha, just a fixed value of alpha, and getting that to be well-tuned has a huge impact. Learning rate decay does help. Sometimes it can really help speed up training, but it is a little bit lower down my list when in terms of the things I would try. But next week, when we talk about hyperparameter tuning, you see more systematic ways to organize all of these hyperparameters and how to efficiently search amongst them. So that's it for learning rate decay. Finally, I also want to talk a little bit about local optima and saddle points in neural networks, so you can have a little bit better intuition about the types of optimization problems your optimization algorithm is trying to solve when you're trying to train these neural networks. Let's go on to the next video to see that. In the early days of deep learning, people used to worry a lot about the optimization algorithm getting stuck in bad local optima. But as the theory of deep learning has advanced, our understanding of local optima is also changing. Let me show you how we now think about local optima and problems with the optimization problem in deep learning. So this was a picture people used to have in mind when they worried about local optima. Maybe you're trying to optimize some set of parameters, I'm going to call them W1 and W2, and the height of the surface is the cost function. So in this picture, it looks like there are a lot of local optima, in all those places, and it'd be easy for gradient descent or one of the other algorithms to get stuck on a local optimum rather than find its way to a global optimum. It turns out that if you're plotting a figure like this in 2 dimensions, then it's easy to create plots like this with a lot of different local optima. And these very low dimensional plots used to guide our intuition. But this intuition isn't actually correct. It turns out if you train a neural network, most points of 0 gradients are not local optima, like points like this. Instead, most points of 0 gradient in a cost function are actually saddle points. So that's a point with a 0 gradient. Again, this is maybe W1, W2, and the height is the value of the cost function J. But informally, a function in a very high dimensional space, if the gradient is 0, then in each direction it can either be a convex light function or a concave light function. And if you're in, say, a 20,000 dimensional space, then for it to be a local optima, all 20,000 directions need to look like this. And so the chance of that happening is maybe very small, maybe 2 to the minus 20,000. Instead, you're much more likely to get some directions where the curve bends up, like so, as well as some directions where the curve function is bending down, rather than have them all bend upwards. So that's why in very high dimensional spaces, you're actually much more likely to run into a saddle point, like that shown on the right, than the local optimum. Oh, and as for why this surface is called a saddle point, if you can picture, maybe this is a sort of saddle you put on a horse, right? So maybe if this is a horse, I guess there's the head of a horse, there's the eye of a horse, I guess. And, right, well, not a great drawing of a horse, but you get the idea. Then you, the rider, would sit here in the saddle. So that's why this point here, where the derivative is 0, that point is called a saddle point. It's really the point on the saddle where you would sit, I guess, and that happens to have, derivative 0. And so one of the lessons we learn in history of deep learning is that a lot of our intuitions about low-dimensional spaces, like what you can plot on the left, they really don't transfer to the very high-dimensional spaces that our learning algorithms are operating over. Because if you have 20,000 parameters, then J is really a function over a 20,000 dimensional vector, and you're much more likely to see saddle points than local optimum. If local optima aren't a problem, then what is a problem? It turns out that plateaus can really slow down learning, and a plateau is a region where the derivative is close to 0 for a long time. So if you're here, then gradient descent will move down this surface, and because the gradient is 0 or near 0, the surface is quite flat. You can actually take a very long time, to slowly find your way to maybe this point on the plateau, and then because of a random perturbation to the left or right, maybe then finally, I'm going to switch pen colors for clarity, your algorithm can then find its way off the plateau. But that to take this very long, slow path before it's found its way here, and then could get off this plateau. So the takeaways from this video are, first, you're actually pretty unlikely to get stuck in bad local optima so long as you're training a reasonably large neural network. So you have a lot of parameters, and the cost function J is defined over a relatively high dimensional space. But second, that plateaus are a problem and they can actually make learning pretty slow. And this is where algorithms like Momentum or RMSprop or Adam can really help your learning algorithm as well. And these are scenarios where more sophisticated optimization algorithms, such as Adam, can actually speed up the rate at which you could move down the plateau and then get off the plateau. So because neural networks are solving optimization problems over such high dimensional spaces, to be honest, I don't think anyone has great intuitions about what these spaces really look like, and our understanding of them is still evolving. But I hope this gives you some better intuition about the challenges that the optimization algorithms may face. So congratulations on coming to the end of this week's content. Please take a look at this week's quiz as well as the programming exercise. I hope you enjoy practicing some of these ideas with this week's programming exercise, and I look forward to seeing you at the start of next week's videos. Welcome, Yuanqing. I'm really glad you could join us today.
Sure.
Today you're the head of Baidu Research, and
Right.
when the Chinese government, the government of China, was looking for someone to start up and build a national deep learning research lab,
Right.
they tapped you to help start this thing. So, arguably, I think maybe you're the #1 deep learning person in the entire country of China. So I'd love to ask you a lot of questions about your work, but before that, I want to hear about your personal story. So how did you end up, getting to do this work that you do?
Yeah, so I before my PhD program, my major was in kind of optics, so it's more like in physics. So I think I had a very good kind of background, like a very good background on math. Then after I came to US, then I was thinking like what kind of major I'm gonna take for my PhD program. I was thinking that whether I could go for optics or go for something else, because back to like early 2000, I think nano technology was very, very hot. But I was thinking that probably I should look at something like even more exciting. And there's a good chance that I was taking some classes at UPenn, and I got to know Dan Li. So later he became my PhD advisor. So, and I was thinking like machine learning was a great thing to do. And I got really excited, and I changed my major. So I did my PhD at UPenn, like majoring in machine learning. Yeah. And so that kind of actually is, I was there for 5 years, and that was kind of really exciting. And I think I learned lots of things from scratch. Lots of algorithms, even like PCAs. I didn't know those before. Yeah, it was kind of, I feel like I was learning new things every day. So it was very, very exciting experience for me.
It was one of those teams with a lot of stars, although just did a lot of work, and it was underappreciated for its time.
Right, that's right. Yeah, so I think NC was exciting place, and I was there at the beginning as a researcher. Again, I also like feel like, wow, I learned lots of things. And I actually later at NEC, I kind of started working on computer vision. I actually started working on computer vision very late, relatively late, yeah. And the first thing I did was I participated in the ImageNet Challenge. That's the first year of ImageNet Challenge. I was kind of managing a team to work on the project. It was lucky, we were quite lucky that we were quite strong, and we at the end we actually got the #1 place, overwhelming #1 place in the context.
So you were the first ever in the world ImageNet competition winner.
Right. Yeah, and I was the person that did the presentation at the workshop. Yeah, so I was that was really nice experience for me, and that actually get me into these very large scale kind of computer vision tasks. Yeah, and so I have been working on these very large scale problems since then. So when these your CAT paper, New York Times CAT come out, and also later on like this AlexNet come out, it really blew my mind. Actually, I thought like, wow, deep learning is so powerful, and I think since then I invest lots of effort, I think, to work on those.
So as a head of China's National Research Lab on Deep Learning, there must be a lot of exciting activities going on there.
Right.
So for the global audience, watching this, what should they know about what's happening with this national lab?
The mission of this National Engineering Lab is to build a very large deep learning platform, and probably hope to be the biggest one, at least the biggest one in China. And on this platform, we would offer people like a deep learning framework like Paddle, and we offer people the very large scale computing resource, and we will also offer people very large, like very big kind of data, right? And if people are able to kind of to develop or research or develop a kind of good technology on this platform, we will also offer them like a big applications. So for example, the technology can be plugged into some big applications in Baidu, so that the technology could get iterated and improved. Yeah. So we believe that combining those combining those resources all together, I think this is going to be a very powerful platform. Let me also give you kind of one example on this. For example, like right now, if we publish a paper, let's say a researcher publish a paper, if someone want to reproduce it, then they need to kind of, the best thing to do is probably the person will provide the code somewhere, and you could download that code to your computer, and you also try to find the data set somewhere, and you probably you probably also need to get the good configuration of your kind of computing resource to run it smoothly, right? So this easily kind of take you some efforts. At this deep national lab, things will become much easier. So if someone using this platform to write the paper, to do the work and write the paper, and they will have the code on this platform, and the computing structure is already set up for this code, and the data is there too. So basically, you just need a command line to reproduce the result. So this is a huge, I think, is a bigger kind of relief for lots of kind of reproducibility issues in computer science. So you just kind of, just a few seconds, you start learning something like you see in the paper. Yeah, so this is extremely powerful. So so this is just one example that we are working on, like to make sure that we are providing like a very powerful platform to the community and to the industry.
That's amazing. That would really speed up deep learning research.
Right. Yeah.
Can you give a sense of how much resources the Chinese government is putting to back you for this deep learning national lab?
So I think for this national engineering lab, I think the government definitely gonna invest some funding into here to build up the infrastructure. But I think more importantly would be this is gonna be a flagship in China that gonna lead lots of kind of deep learning efforts, like including like a national project and lots of kind of policies and things Yeah, so this actually is extremely powerful. And I think for Baidu, we are really honored to get this lab.
You're somewhat at the heart of deep learning in China.
Yeah.
So there's a lot of activity in China that the global audience, isn't aware of yet and hasn't seen yet.
Right.
So what should people outside China know about deep learning in China?
Yeah, I think in China, especially in the past few years, I think the deep learning powered product and service is really booming. Ranging from search engines to face recognition to surveillance to e-commerce, lots of places. I think they are investing big effort in the deep learning, and also they are really make use of those technology to make the business much more powerful. Yeah, and this actually is very important for developing AI technology in general. I think for myself, and also lots of people share this. We believe that actually it's very important to have this we often call the positive loop. Right? For example, you probably when we start out to think of building some technology, then we will have some initial data and we try to develop some initial algorithm. We launch some initial product, right? Product or service. Then after that we get the data from users, and after we get more data, then we'll develop more. We will develop better algorithms, right? Because we see more data, we know what will be the better algorithm. So we have more data and better algorithm. We're able to have better technology for the product and service, and then definitely we hope we'll be able to attract more users, right? Because of the technology is better, and we'll get more data. So this is a very good positive loop, and it's very special actually for AI related technologies, right? I mean, for like traditional technology like laser that I was working on that before. So it's more like the growth of the technology going to be more linear. But for this AI technology, actually, because of this positive loop, you can imagine that definitely at a certain point you will come with very fast growth of the technology. Yeah. And this actually is super important. And when we're designing the research and development, when we design our R&D, but we work on the direction that we're able to get to this quick kind of improving period, right? If we are not able to, if our business and we are not able to, our whole business is not able to form this positive loop, or if we are not able to form this kind of strong positive loop, then this direction probably should not work on, because someone else who have a strong business to form this strong loop, then they will get to this kind of a phase much more quicker than you are. So this actually is a very important logic for us when we're looking at it, like I say, hey, in this company, what direction we should work on and what direction we should not work on. This definitely is a very important factor we should look at.
Today, both in China and in the US and globally, there are a lot of people wanting to enter deep learning and wanting to enter AI.
Right.
What advice would you have for someone that wants to get into this field?
So nowadays, definitely, I think people who start with open source frameworks, I think that's extremely powerful to many starters. I think when I was starting my deep learning study, there was not much a open source resource. I think nowadays, in AI or especially in deep learning, there is a very good community outlet, right? And there are multiple very good deep learning frameworks to start with, like a TensorFlow, a Caviar, like now it's called Caviar 2, right? And in China we have very good Paddle, right? And those are, and even for most of those online, they have lots of courses to teach you how to use those. And also nowadays also there are many publicly available benchmark, and the people could see, hey, very kind of skillful or very experienced people, how well they could do on those benchmark. So basically, to get familiar with deep learning, I think those are very good starting point.
How did you gain that understanding?
So actually, I do it in an opposite way. Right? I kind of learn. I mentioned I learn PCA. I learn like LDA and all those like before I learn deep learning actually. Right. So so basically that also is a good way. I feel like we kind of lay down lots of foundations. Right. And we learn graphical model. Right. So these are all kind of important. Although right now. Deep learning is become very dominant, but knowing those actually give you very good intuition about how deep learning works. And one day probably there's a connection of deep learning to those like a framework or approach. I think there's already lots of connections, and those actually make deep learning richer, right? I mean, there are richer ways of doing deep learning, right? Yeah. So I feel like. It's good to start with those kind of open source platforms. Those are definitely extremely powerful resource. But meanwhile, I also suggest like you also to learn those basic things about machine learning.
So thank you. That was fascinating. Even though I've known you for a long time, there are a lot of details you're thinking that I didn't realize until now. So thank you very much.
Thank you so much for having me.
Hi, and welcome back. You've seen by now that training a neural net can involve setting a lot of different hyperparameters. Now, how do you go about finding a good setting for these hyperparameters? In this video, I want to share with you some guidelines, some tips for how to systematically organize your hyperparameter tuning process, which hopefully will make it more efficient for you to converge on a good setting of the hyperparameters. One of the painful things about training deep nets is the sheer number of hyperparameters you have to deal with, ranging from the learning rate alpha to the momentum term beta, if you're using momentum, or the hyperparameters for the Adam optimization algorithm, which were beta 1, beta 2, and epsilon. Maybe you have to pick the number of layers. Maybe you have to pick the number of hidden units for the different layers. And maybe you want to use learning rate decay, so you don't just use a single learning rate alpha. And then, of course, you might need to choose the mini batch size. So it turns out some of these hyperparameters are more important than others. For most learning applications, I would say alpha, the learning rate, is the most important hyperparameter to tune. Other than alpha, a few other hyperparameters I tend to would maybe tune next would be maybe the momentum term. I say 0.9 is a good default. I'd also tune the mini batch size to make sure that your optimization algorithm is running efficiently. Often I'll also fiddle around with the hidden units. Of the ones I've circled in orange, these are really the three that I would consider second in importance to the learning rate alpha. And then third in importance, after fiddling around with the others, the number of layers can sometimes make a huge difference, and so can learning rate decay. And then when using the Adam algorithm, I actually pretty much never tune beta 1, beta 2, and epsilon. Pretty much always use 0.9, 0.999, and 10 to the minus 8. Although you can try tuning those as well if you wish. But hopefully this gives you some rough sense of what hyperparameters might be more important than others. Alpha, most important for sure. Followed maybe by the ones I've circled in orange, followed maybe by the ones I circled in purple. But this isn't a hard and fast rule, and I think other deep learning practitioners may well disagree with me or have different intuitions on these. Now, if you're trying to tune some set of hyperparameters, how do you select a set of values to explore? In earlier generations of machine learning algorithms, if you had two hyperparameters, which I'm calling hyperparameter 1 and hyperparameter 2 here, it was common practice to sample the points in a grid, like so, and systematically explore these values. Here I'm placing down a 5 by 5 grid. In practice, it could be more or less than a 5 by 5 grid. But you try out, in this example, all 25 points, and then pick whichever hyperparameter works best. And this practice worked okay when the number of hyperparameters was relatively small. In deep learning, what we tend to do, and what I recommend you do instead, is choose the points at random. So go ahead and choose maybe the same number of points, right? 25 points. And then try out the hyperparameters on this randomly chosen set of points. And the reason you do that is that it's difficult to know in advance which hyperparameters are going to be the most important for your problem. And as you saw in the previous slide, some hyperparameters are actually much more important than others. So to take an example, let's say hyperparameter 1 turns out to be alpha, the learning rate. And to take an extreme example, let's say that hyperparameter 2 was that value epsilon that you have in the denominator of the Adam algorithm. So your choice of alpha matters a lot and your choice of epsilon hardly matters. So if you sample on a grid, then you've really tried out 5 values of alpha, and you might find that all of the different values of epsilon give you essentially the same answer. So you've now trained 25 models and only gotten to try out 5 values for the learning rate alpha, which is the thing that's really important. Whereas in contrast, if you were to sample at random, then you will have tried out 25 distinct values of the learning rate alpha, and therefore you'd be more likely to find a value that works really well. I've explained this example using just 2 hyperparameters. In practice, you might be searching over many more hyperparameters than this. So if you have, say, 3 hyperparameters, I guess instead of searching over a square, you're searching over a cube, where this 3rd dimension is hyperparameter 3, and then by sampling within this 3-dimensional cube, you get to try out a lot more values of each of your 3 hyperparameters. And in practice, you might be searching over even more hyperparameters than 3, and sometimes it's just hard to know in advance which ones turn out to be the really important hyperparameters for your application. And sampling at random rather than in a grid ensures that you're more richly exploring the set of possible values for the most important hyperparameters, whatever they turn out to be. When you sample hyperparameters, another common practice is to use a coarse-to-fine sampling scheme. So let's say in this 2-dimensional example that you sampled these points, and maybe you found that this point worked the best, and maybe a few other points around it tended to work really well. Then in the coarse-to-fine scheme, what you might do is zoom in to a smaller region of the hyperparameters and then sample more densely within this space. Maybe again at random, but to then focus more resources on searching within this blue square if you're suspecting that the best setting of the hyperparameters may be in this region. So after doing a coarse sample of this entire square, if that tells you to then focus on a smaller square, you can then sample more densely in this smaller square. So this type of a coarse-to-fine search is also frequently used. And by trying out these different values of the hyperparameters, you can then pick whatever value allows you to do best on your training set objective, or does best on your development sets, or whatever you're trying to optimize in your hyperparameter search process. So I hope this gives you a way to more systematically organize your hyperparameter search process. The 2 key takeaways are use random sampling, not a grid search, and consider, optionally, but consider implementing a coarse-to-fine search process. But there's even more to hyperparameter search than this. Let's talk more in the next video about how to choose the right scale on which to sample your hyperparameters. In the last video, you saw how sampling at random over the range of hyperparameters can allow you to search over the space of hyperparameters more efficiently. But it turns out that sampling at random doesn't mean sampling uniformly at random over the range of valid values. Instead, it's important to pick the appropriate scale on which to explore the hyperparameters. In this video, I want to show you how to do that. Let's say that you're trying to choose the number of hidden units NL for a given layer L, and let's say that you think a good range of values is somewhere from 50 to 100. In that case, if you look at the number line from 50 to 100, maybe picking some number of values at random within this number line is a pretty reasonable way to search for this particular hyperparameter. Or if you're trying to decide on the number of layers in your neural network, we're calling that capital L, maybe you think the total number of layers should be somewhere between 2 to 4. Then sampling uniformly at random among 2, 3, and 4 might be reasonable, or even using a grid search where you explicitly evaluate the values 2, 3, and 4 might be reasonable. So these were a couple examples where sampling uniformly at random over the range you're contemplating might be a reasonable thing to do. But this is not true for all hyperparameters. Let's look at another example. Say you're searching for the hyperparameter alpha, the learning rate, and let's say that you suspect 0.0001 might be on the low end, or maybe it could be as high as 1. Now, if you draw the number line from 0.0001 to 1 and sample values at random, uniformly at random over this number line, or about 90% of the values you sample will be between 0.1 and 1. So you're using 90% of the resources to search between 0.1 and 1, and only 10% of the resources to search between 0.0001 and 0.1. So that doesn't seem right. Instead, it seems more reasonable to search for hyperparameters on the log scale, where instead of using a linear scale, you'd have 0.0001 here, and then 0.001, 0.01, 0.1, and then 1. And you instead sample uniformly at random on this type of logarithmic scale. Now you have more resources dedicated to searching between 0.0001 and 0.001, and between 0.001 and 0.01, and so on. So in Python, the way you implement this is let r equals -4 times np.random.rand, and then a randomly chosen value of alpha would be alpha equals 10 to the power of r. So after this first line, r will be a random number between -4 and 0, and so alpha here will be between 10 to the -4 and 10 to the 0. So 10 to the -4 is this left thing, this 10 to the -4, and 1 is 10 to the 0. In a more general case, if you're trying to sample between 10 to the A to 10 to the B on the log scale, and in this example, this is 10 to the A, and you can figure out what A is by taking the log base 10 of 0.0001, which is going to tell you A is -4. And this value on the right, this is 10 to the B, and you can figure out what B is by taking log base 10 of 1, which tells you B is equal to 0. So what you do is then sample R uniformly at random between A and B. So in this case, R would be between -4 and 0, and you can set alpha, or your randomly sample hyperparameter value, as 10 to the R. Okay, so just to recap, to sample on the log scale, you take the low value, take logs to figure out what is A, take the high value, take a log to figure out what is B. So you're now trying to sample from 10 to the A to 10 to the B on a log scale. So you set R uniformly at random between A and B, and then you set the hyperparameter to be 10 to the R. So that's how you implement sampling on this logarithmic scale. Finally, one other tricky case is sampling the hyperparameter beta used for computing exponentially weighted averages. So let's say you suspect that beta should be somewhere between 0.9 to 0.999. Maybe this is the range of values you want to search over. So remember that when computing exponentially weighted averages, using 0.9 is like averaging over the last 10 values, kind of like taking the average of 10 days temperature, whereas using 0.999 is like averaging over the last 1,000 values. So similar to what we saw on the last slide, if you want to search between 0.9 and 0.999, it doesn't make sense to sample on the linear scale, right, uniformly at random between 0.9 and 0.999. So a better way to think about this is that we want to explore the range of values for 1 minus beta, which is going to now range from 0.1 to 0.001. And so we'll sample between beta, take on values from 0.1 to maybe 0.1 to 0.001. So using the method we had figured out on the previous slide, this is 10 to the -1, this is 10 to the -3. Notice on the previous slide we had the small value on the left and the large value on the right, but here we have it reversed. We have the large value on the left and the small value on the right. So what you do is you sample R uniformly at random from -3 to -1, and you set 1 minus beta equals 10 to the r, and so beta equals 1 minus 10 to the r, and this becomes your randomly sampled value of your hyperparameter chosen on the appropriate scale. And hopefully this makes sense in that this way you spend as much resources exploring the range 0.9 to 0.99 as you would exploring 0.99 to 0.999. So if you want a slightly more formal mathematical justification for why we're doing this, right? Why is it such a bad idea to sample on a linear scale? It is that when beta is close to 1, the sensitivity of the results you get changes even with very small changes to beta. So if beta goes from 0.9 to 0.9005, it's no big deal. This is hardly any change in your results. But if beta goes from 0.999 to 0.9995, this will have a huge impact on exactly what your algorithm is doing, right? In both of these cases, it's averaging over roughly 10 values, but here it's gone from an exponentially weighted average over about 1,000, the last 1,000 examples to now the last 2,000 examples. And it's because that formula we had, 1 over 1 minus beta, this is very sensitive to small changes in beta when beta is close to 1. So what this whole sampling process does is it causes you to sample more densely in the regime of when beta is close to 1, or alternatively when 1 minus beta is close to 0, so that you can be more efficient in terms of how you distribute the samples to explore the space of possible outcomes more efficiently. So I hope this helps you select the right scale on which to sample the hyperparameters. In case you don't end up making the right scaling decision on some hyperparameter choice, don't worry too much about it. Even if you sample on a uniform scale where some other scale would have been superior, you might still get okay results, especially if you use a coarse-defined search, so that in later iterations, you focus in more on the most useful range of hyperparameter values to sample. I hope this helps you with your hyperparameter search. In the next video, I also want to share with you some thoughts on how to organize your hyperparameter search process that I hope will make your workflow a bit more efficient. You've now heard a lot about how to search for good hyperparameters. Before wrapping up our discussion on hyperparameter search, I want to share with you just a couple final tips and tricks for how to organize your hyperparameter search process. Deep learning today is applied to many different application areas, and that intuitions about hyperparameter settings from one application area may or may not transfer to a different one. There is a lot of cross-fertilization among different applications domains. So for example, I've seen ideas developed in the computer vision community, such as ConvNets or ResNets, which we'll talk about in a later course, successfully applied to speech. And I've seen ideas that were first developed in speech successfully applied in NLP, and so on. So one nice development in deep learning is that people from different application domains do read increasingly research papers from other application domains to look for inspiration for cross-fertilization. In terms of your setting for the hyperparameters though, I've seen that intuitions do get stale. So even if you work on just one problem, say logistics, you might have found a good setting for the hyperparameters and kept on developing your algorithm, or maybe seen your data gradually change over a course of several months, or maybe just upgraded the servers in your data center. And because of those changes, the best setting of your hyperparameters can get stale. So I recommend maybe just retesting or re-evaluating your hyperparameters at least once every several months to make sure that you're still happy with the values you have. Finally, in terms of how people go about searching for hyperparameters, I see maybe two major schools of thought, or maybe two major different ways in which people go about it. One way is if you babysit one model, and usually you do this if you have maybe a huge data set, but not a lot of computational resources, not a lot of CPUs and GPUs, so you can basically afford to train only one model or a very small number of models at a time. In that case, you might gradually babysit that model even as it's training. So for example, on day 0, you might initialize your parameters at random and then start training. And you gradually watch your learning curve, maybe the cost function J or your depth set error or something else, gradually decrease over the first day. then at the end of day 1, you might say, gee, it looks like it's learning quite well. I'm going to try increasing the learning rate a little bit and see how it does. And then maybe it does better, and then that's your day 2 performance. And after 2 days, you say, oh, okay, it's still doing quite well. Maybe I'll further the momentum term a bit or decrease the learning rate a little bit now. And then you're now into day 3. And every day you kind of look at it and try nudging up and down your parameters. And maybe on one day you found your learning rate was too big, so you might go back to the previous day's model and so on. But you're kind of babysitting the model one day at a time, even as it's training over a course of many days or over the course of several different weeks. So that's one approach, and people that babysit one model, that is watching a performance and patiently nudging the learning rate up or down, that's usually what happens if you don't have enough computational capacity to train a lot of models at the same time. The other approach would be if you train many models in parallel. So you might have some setting of the hyperparameters and just let it run by itself, either for a day or even for multiple days. Maybe get some learning curve like that. And this could be a plot of the cost function J, or cost of your training error, or cost of your depth set error, but some metric that you're tracking. And then at the same time, you might start up a different model with a different setting of the hyperparameters. And so your second model might generate a different learning curve, maybe one that looks like that, or looks like that one looks better. And at the same time, you might train a third model, which might generate a learning curve that looks like that. And another one that maybe this one diverges, so it looks like that, and so on. But you might train many different models in parallel, where these orange lines are different models. Right? And so this way you can try a lot of different hyperparameter settings and then just maybe quickly at the end pick the one that works best. Looks like in this example it was maybe this curve that looked best. So to make an analogy, I'm going to call the approach on the left the panda approach. When pandas have children, they have very few children, usually one child at a time, and then they really put a lot of effort into making sure that the baby panda survives. So that's really babysitting, one model or one baby panda. Whereas the approach on the right is more like what fish do. I'm going to call this the caviar strategy. There's some fish that lay over 100 million eggs in one season, in one mating season. But the way fish reproduce is they lay a lot of eggs and don't pay too much attention to any one of them, but just see that hopefully one of them, or maybe a bunch of them, will do well. So I guess this is really the difference between how mammals reproduce versus how fish and a lot of reptiles reproduce. But I'm going to call it the panda approach versus the caviar approach, since that's more fun and memorable. So the way to choose between these two approaches is really a function of how much computational resources you have. If you have enough computers to train a lot of models in parallel, then by all means take the caviar approach and try a lot of different hyperparameters and see what works. But in some application domains, I see this in some online advertising settings as well as in some computer vision applications where there's just so much data and the models you want to train are so big that it's difficult to train a lot of models at the same time. It's really application dependent, of course, but I've seen those communities use the panda approach a little bit more, where you're kind of babying a single model along and nudging the parameters up and down and trying to make this one model work. Although, of course, even the panda approach, having trained one model and then seen it work or not work, maybe in the second week or the third week, maybe you actually initialize a different model and then, baby that one along. Just like even pandas, I guess, can have multiple children in their lifetime, even if they have only one or a very small number of children at any one time. So hopefully this gives you a good sense of how to go about the hyperparameter search process. Now, it turns out that there's one other technique that can make your neural network much more robust to the choice of hyperparameters. It doesn't work for all neural networks, but when it does, it can make the hyperparameter search much easier and also make training go much faster. Let's talk about this technique in the next video. In the rise of deep learning, one of the most important ideas has been an algorithm called batch normalization, created by two researchers, Sergei Ioffe and Christian Szegedy. Batch normalization makes your hyperparameter search problem much easier. It makes your neural network much more robust to the choice of hyperparameters. There's a much bigger range of hyperparameters that work well, and it'll also enable you to much more easily train even very deep networks. Let's see how batch normalization works. When training a model, such as logistic regression, you might remember that normalizing the input features can speed up learning. So you can compute the means, subtract off the means from your training set, compute the variances. This sum over xi squared, this is a element y squaring. Right, and then normalize your data set according to the variances. And we saw in an earlier video how this can turn the contours of your learning problem from something that might be very elongated to something that is more round and easier for an algorithm like gradient descent to optimize. So this works in terms of normalizing the input feature values to a neural network or to logistic regression. Now, how about a deeper model? You have not just input features x, but in this layer you have activations A1, in this layer you have activations A2, and so on. So if you want to train the parameters, say W3, B3, then won't it be nice if you can normalize the mean and variance of A2 to make the training of W3, B3 more efficient? In the case of logistic regression, we saw how normalizing x1, x2, x3 maybe helps you train W and B more efficiently. So here the question is, for any hidden layer, can we normalize the values of A, let's say A2 in this example, but really any hidden layer, so as to train W3, B3 faster, right? Since A2 is the input to the next layer that therefore affects your training of W3 and B3. So this is what batch norm does, batch normalization, or batch norm for short does. Although technically we'll actually normalize the values of not A2, but Z2. There is some debate in the deep learning literature about whether you should normalize the value before the activation function, so Z2, or whether you should normalize the value after applying the activation function, A2. In practice, normalizing Z2 is done much more often, so that's the version I'll present and what I would recommend you use as the default choice. So here is how you would implement batch norm. Given some intermediate values in your neural net, let's say that you have some hidden unit values, Z1 up to Zm, and this is really from some hidden layer, so it'd be more accurate to write this as Z for some hidden layer I for I equals 1 through m, but to reduce writing, I'm going to omit this square bracket L just to simplify the notation on this slide. So given these values, what you do is compute the mean as follows. Again, all this is specific to some layer L, but I'm omitting the square bracket L. And then you compute the variance using pretty much the formula you would expect. And then you would take each of the zi's and normalize it. So get zi normalized by subtracting off the mean and dividing by the standard deviation. For numerical stability, we usually add epsilon to the denominator like that, just in case sigma squared turns out to be 0 in some estimate. And so now we've taken these values z and normalized them to have mean 0 and standard unit variance. So every component of z has mean 0 and variance 1. But we don't want the hidden units to always have mean 0 and variance 1. Maybe it makes sense for hidden units to have a different distribution. So what we'll do instead is compute, I'm going to call this z tilde equals gamma zi norm plus beta. And here, gamma and beta are learnable parameters of your model. So if you're using gradient descent or some other algorithm like gradient descent with momentum or RMSprop or Atom, you would update the parameters gamma and beta just as you would update the weights of your neural network. Now, notice that the effect of gamma and beta is that it allows you to set the mean of z tilde to be whatever you want it to be. In fact, if gamma equals square root sigma squared plus epsilon, so if gamma were equal to this denominator term, and if beta were equal to mu, so with this value up here, then the effect of gamma z norm plus beta is that it would exactly invert this equation. So if this is true, then actually z tilde I is equal to zi. And so by an appropriate setting of the parameters gamma and beta, this normalization step, that is these four equations, is just computing essentially the identity function. But by choosing other values of gamma and beta, this allows you to make the hidden unit values have other means and variances as well. And so the way you fit this into your neural network is, whereas previously you were using these values z1, z2, and so on, you would now use z tilde I instead of zi for the later computations in your neural network. And we want to put back in this square bracket L, to explicitly denote which layer it is in. You can put it back there. So the intuition I hope you'll take away from this is that we saw how normalizing the input features X can help learning on a neural network. And what batch norm does is it applies that normalization process not just to the input layer, but to the values even deep in some hidden layer in the neural network. So you apply this type of normalization to normalize the mean and variance of some of your hidden units values Z. But one difference between the training input and these hidden unit values is you might not want your hidden unit values to be forced to have mean 0 and variance 1. For example, if you have a sigmoid activation function, you don't want your values to always be clustered here. You might want them to have a larger variance or have a mean that's different than 0 in order to better take advantage of the nonlinearity of the sigmoid function rather than have all your values be in just this linear regime. So that's why with the parameters gamma and beta, you can now make sure that your zi values have the range of values that you want. But what it does really is it ensures that your hidden units have standardized mean and variance, where the mean and variance are controlled by two explicit parameters, gamma and beta, which the learning algorithm can set to whatever it wants. So what it really does is it normalizes the mean and variance of these hidden unit values, really the zi's, to have some fixed mean and variance. And that mean and variance could be 0 and 1, or it could be some other value, and is controlled by these parameters gamma and beta. So I hope that gives you a sense of the mechanics of how to implement batch norm, at least for a single layer in a neural network. In the next video, I want to show you how to fit batch norm into a neural network, even a deep neural network, and how to make it work for the many different layers of a neural network. And after that, we'll give some more intuition about why batch norm could help you train your neural networks. So in case why it works still seems a little bit mysterious, stay with me, and I think in 2 videos from now, we'll really make that clearer. So you've seen the equations for how to implement batch norm for maybe a single hidden layer. Let's see how it fits into the training of a deep network. So let's say you have a neural network like this. You've seen me say before that you can view each hidden unit as computing 2 things. First, it computes Z, and then it applies the activation function to compute A. And so you can think of each of these circles as representing a 2-step computation. And similarly for the next layer, that's Z2, 1 and A2, 1, and so on. So if you were not applying batch norm, you would have an input X, feed into the first hidden layer, and then first compute Z1. And this is governed by the parameters W1 and B1. And then ordinarily, you would feed Z1 into the activation function to compute A1. But what we'll do in batch norm is take this value Z1 and apply batch norm, sometimes abbreviated Bn to it, and that's going to be governed by parameters beta 1 and gamma 1. And this will give you this new normalized value Z1. And then you feed that to the activation function to get A1, which is G1 applied to z tilde 1. Now, you've done the computation for the first layer, where this batch norm step really occurs, in between the computation from z and a. Next, you take this value a1 and use it to compute z2, and so this is now governed by w2, b2. And similar to what you did for the first layer, you would take z2 and apply it through batch norm. I'm going to abbreviate that bn now. This is governed by batch norm parameters specific to the next layer, so beta 2, gamma 2. And now this gives you z tilde 2, and you use that to compute a2 by applying the activation function, and so on. So once again, the batch norm step kind of happens between computing z and computing a. And the intuition is that instead of using the unnormalized value z, you're going to use the normalized value z tilde. That's in the first layer. In the second layer as well, instead of using the unnormalized value z2, you're going to use the mean and variance normalized values z tilde 2. So the parameters of your network are going to be w1, b1. It turns out we'll get rid of the b parameters, but we'll see why in the next slide. But for now, imagine your parameters are the usual w1, b1 through wl, bl. And we've added to this neural network additional parameters, beta 1, gamma 1, beta 2, gamma 2, and so on, for each layer in which you are applying batch norm. For clarity, note that these betas here, these have nothing to do with the hyperparameter beta that we had for momentum or for the computing the various exponentially weighted averages. The authors of the Adam paper had used beta in their paper to denote that hyperparameter. The authors of the batch norm paper had used beta to denote this parameter, but these are two completely different betas. I decided to stick with beta in both cases in case you read the original papers, but the beta 1, beta 2, and so on that batch norm tries to learn is a different beta than the hyperparameter beta used in momentum and in the Adam and RMSprop algorithms. But so now that these are the new parameters of your algorithm, you would then use whatever optimization you want, such as gradient descent, in order to implement it. So for example, you might compute d beta l for a given layer, and then update the parameters. Beta gets updated as beta minus the learning rate times d beta l. And you can also use Adam or RMSprop or momentum in order to update the parameters beta and gamma, not just gradient descent. And even though in the previous video I'd explained what the batch norm operation does, computes means and variances and subtracts and divides by them, if you're using a deep learning programming framework, usually you won't have to implement the batch norm step or the batch norm layer yourself. In some of the programming frameworks, it can be sort of one line of code. So for example, in the TensorFlow framework, you can implement batch normalization with this function. We'll talk more about programming frameworks later, but in practice, you might not end up needing to implement all these details yourself, but it's still worth knowing how it works so that you can get a better understanding of what your code is doing. But implementing batch norm is often, something like one line of code in the deep learning frameworks. Now, so far, we've talked about batch norm as if you were training on your entire training set at a time, as if you were using batch gradient descent. In practice, batch norm is usually applied with mini batches of your training set. So the way you actually apply batch norm is you take your first mini batch and compute Z1, same as we did on the previous slide, using the parameters W1, B1. And then you take just this mini batch and compute the mean and variance of the Z1s on just this mini batch. And then batch norm would subtract by the mean and divide by the standard deviation, and then rescale by beta 1, gamma 1 to give you Z1. And all this is on the first mini batch. Then you'll apply the activation function, to get A1, and then you compute Z2 using W2, B2, and so on. So you do all this in order to perform one step of, say, gradient descent on the first mini batch, and then you go to the second mini batch, X2, and you do something similar, right, where you now compute Z1 on the second mini batch, and then use batch norm to compute Z1 tilde. And so here in this batch norm step, you'd be normalizing Z tilde using just the data in your second mini batch. So this batch norm step here is looking at the examples in your second mini batch, computing the mean and variances of the Z1s on just that mini batch, and then rescaling by beta and gamma to get Z tilde, and so on. And you do this with the third mini batch and keep training. Now, there's one detail to the parameterization that I want to clean up, which is previously I said that the parameters was WL, BL for each layer, as well as beta L and gamma L. Now, notice that the way ZL is computed is as follows. ZL equals WL times A of L minus 1 plus B of L. But what batch norm does is it's going to look at the mini batch and normalize ZL to first have mean 0 and standard variance, and then a rescale by beta and gamma. But what that means is that whatever is the value of BL is actually going to just get subtracted out. Because during that batch norm normalization step, you're going to compute the means of the ZLs and then subtract out the mean. And so adding any constant to all of the examples in a mini batch, it doesn't change anything, because any constant you add will get cancelled out by the mean subtraction step. So if you're using batch norm, you can actually eliminate that parameter. Or if you want, think of it as setting it permanently to 0. So then the parameterization becomes ZL is just WL times AL minus 1, and then you compute ZL normalized, and when you compute Z tilde equals gamma ZL plus beta, you end up using this parameter beta L in order to decide what's the mean of Z tilde L, which is what gets passed to the next layer. So just to recap, because batch norm zeroes out the mean of these ZL values in the layer, there's no point having this parameter BL, and so you might as well get rid of it, and instead is sort of replaced by beta L, which is a parameter that controls, that ends up affecting the shift or the bias terms. Finally, remember that the dimension of ZL, I guess if you're doing this on one example, is going to be NL by 1, and so BL had dimension NL by 1 if NL is the number of hidden units in layer L. And so the dimension of beta L and gamma L is also going to be NL by 1, because that's the number of hidden units you have. You have NL hidden units, and so beta L and gamma L are used to scale the mean and variance of each of the hidden units to whatever the network wants to set them to. So let's put it all together and describe how you can implement gradient descent using batch norm. Assuming you're using mini batch gradient descent, you iterate for t equals 1 to the number of mini batches. You would implement forward prop on mini batch xt, and doing forward prop in each hidden layer, use batch norm to replace ZL with Z tilde L. And so this ensures that within that mini batch, the values Z end up with some normalized mean and variance. And the values and the version with the normalized mean and variance is this Z tilde L. And then you use backprop to compute dW, dB for all the values of L, d beta, d gamma. Although technically, since we've gotten rid of B, this actually now goes away. And then finally, you update the parameters. So, W gets updated as W minus the learning rate times this as usual. Beta gets updated as beta minus the learning rate times dB, and similarly for gamma. And if you've computed the gradients as follows, you could use gradient descent. That's what I've written down here. But this also works with gradient descent with momentum, or RMSprop, or Atom, where instead of taking this gradient descent update, you could use the updates given by these other algorithms, as we discussed in the previous week's videos. So these other optimization algorithms as well can be used to update the parameters beta and gamma that batch norm added to your algorithm. So I hope that gives you a sense of how you could implement batch norm from scratch if you wanted to. If you're using one of the deep learning programming frameworks, which we'll talk more about later, hopefully you can just call someone else's implementation in the programming framework, which will make using batch norm much easier. Now, in case batch norm still seems a little bit mysterious, if you're still not quite sure why it speeds up training so dramatically, let's go to the next video and talk more about why batch norm really works and what it's really doing. So why does batch norm work? Here's one reason. You've seen how normalizing the input features, the x's, to mean 0 and variance 1, how that can speed up learning. So rather than having some features that range from 0 to 1 and some from 1 to 1,000, by normalizing all the features, input features x, to take on a similar range of values, that can speed up learning. So one intuition behind why batch norm works is this is doing a similar thing, but for the values in your hidden units and not just for your input layer. Now, this is just a partial picture for what batch norm is doing. There are a couple further intuitions that will help you gain a deeper understanding of what batch norm is doing. Let's take a look at those in this video. A second reason why batch norm works is it makes weights later or deeper in the neural network, say the weights for layer 10, more robust to changes to weights in earlier layers of the neural network, say in layer 1. To explain what I mean, let's look at this motivating example. Let's say you're training a network, maybe a shallow network like logistic regression, or maybe a neural network, maybe a shallow network like logistic regression, or maybe a deeper network on our famous cat detection task. But let's say that you've trained your data set on all images of black cats. If you now try to apply this network to data with colored cats, where the positive examples are not just black cats like on the left, but to colored cats like on the right, then your classifier might not do very well. So in pictures, if your training set looked like this, where you have positive examples here and negative examples here, but you were to try to generalize it to a data set where maybe the positive examples are here and the negative examples are here, then you might not expect a model trained on the data on the left to do very well on the data on the right, even though there might be the same function that actually works well, but you wouldn't expect your learning algorithm to discover that green decision boundary just looking at the data on the left. So this idea of your data distribution changing goes by the somewhat fancy name covariate shift. And the idea is that if you learn some x to y mapping, if the distribution of x changes, then you might need to retrain your learning algorithm. And this is true even if the function, the ground truth function mapping from x to y remains unchanged, which it is in this example because the ground truth function is this picture a cat or not? And the need to retrain your function becomes even more acute, or it becomes even worse if the ground truth function shifts as well. So how does this problem of covariate shift apply to a neural network? Consider a deep network like this, and let's look at the learning process from the perspective of this hidden layer, the third hidden layer. So this network has to learn the parameters W3 and B3. And from the perspective of the third hidden layer, it gets some set of values from the earlier layers, and then has to do some stuff to hopefully make the output y hat close to the ground truth value y. So let me cover up the nodes on the left for a second So from the perspective of this third hidden layer, it gets some values. Let's call them A21, A22, A23, and A24. But these values might as well be features, x1, x2, x3, x4. And the job of the third hidden layer is to take these values and find a way to map them to y hat. So you can imagine doing gradient descent so that these parameters w3, b3, as well as maybe w4, b4, and even w5, b5, maybe trying to learn those parameters so the network does a good job mapping from the values I drew in black on the left to the output values y hat. But now let's uncover the left of the network again. The network is also adapting parameters w2, b2, and w1, b1. And so as these parameters change, these values a2 will also change. So from the perspective of the third hidden layer, these hidden unit values are changing all the time, and so it's suffering from the problem of covariate shift that we talked about on the previous slide. So what batch norm does is it reduces the amount that the distribution of these hidden unit values shifts around. And if we were to plot the distribution of these hidden unit values, maybe this is, technically we normalize a z, so this is actually z21 and z22, and I'm just going to plot 2 values instead of 4 values so we can visualize it in 2D. What batch norm is saying is that the values for z21 and z22 can change, and indeed they will change when the neural network updates the parameters in the earlier layers. But what batch norm ensures is that no matter how it changes, the mean and variance of z21 and z22 will remain the same. So even if the exact values of z21 and z22 change, their mean and variance will at least stay, say, mean 0 and variance 1. Or not necessarily mean 0 and variance 1, but whatever value is governed by beta 2 and gamma 2, which if the neural network chooses can force it to be mean 0 and variance 1, or really any other mean and variance. But what this does is it limits the amount to which updating the parameters in the earlier layers can affect the distribution of values that the third layer now sees and therefore has to learn on. And so batch norm reduces the problem of the input values changing. It really causes these values to become more stable so that the later layers of the neural network has more firm ground to stand on. And even though the input distribution changes a bit, it changes less. And what this does is, even as the earlier layers keep learning, the amount that this forces the later layers to adapt to its earlier layers changes is reduced. Or if you will, it weakens the coupling between what the earlier layers parameters has to do and what the later layers parameters have to do. And so it allows each layer of the network to learn by itself, a little bit more independently of other layers. And this has the effect of speeding up learning in the whole network. So I hope this gives some better intuition, but the takeaway is that batch norm means that, especially from the perspective of one of the later layers of the neural network, the earlier layers don't get to shift around as much because they're constrained to have the same mean and variance. And so this makes the job of learning in the later layers easier. It turns out batch norm has a second effect. It has a slight regularization effect. So one non-intuitive thing about batch norm is that each mini batch, say mini batch xt, has the values zt, has the values zl scaled by the mean and variance computed on just that one mini batch. Now, because the mean and variance computed on just that mini batch, as opposed to computed on the entire data set, that mean and variance has a little bit of noise in it because it's computed just on your mini batch of, say, 64 or 128 or maybe 256 or larger training examples. So because the mean and variance is a little bit noisy because it's estimated with just a relatively small sample of data, the scaling process going from ZL to Z tilde L, that process is a little bit noisy as well because it's computed using a slightly noisy mean and variance. So, similar to Dropout, it adds some noise to each hidden layer's activations. The way Dropout adds noise is it takes a hidden unit and it multiplies it by 0 with some probability and multiplies it by 1 with some probability. And so Dropout adds multiplicative noise because it's multiplying by 0 or 1, whereas Batch norm has multiplicative noise because it's scaling by the standard deviation, as well as additive noise because it's subtracting the mean. Where here, the estimates of the mean and the standard deviation are noisy. And so similar to Dropout, Batch norm therefore has a slight regularization effect. Because by adding noise to the hidden units, it's forcing the downstream hidden units not to rely too much on any one hidden unit. And so similar to Dropout, this adds noise to the hidden layers and therefore has a very slight regularization effect. Because the noise added is quite small, this is not a huge regularization effect, and you might choose to use Batch norm together with Dropout, and you might use Batch norm together with Dropout if you want the more powerful regularization effect of Dropout. And maybe one other slightly non-intuitive effect is that if you use a bigger mini batch size, right? So if you use a mini batch size of say 512 instead of 64, by using a larger mini batch size, you're reducing this noise and therefore also reducing this regularization effect. So that's one strange property of Dropout, which is that by using a bigger mini batch size, you reduce the regularization effect. Having said this, I wouldn't really use Batch norm as a regularizer. That's really not the intent of Batch norm, but sometimes it has this extra intended or unintended effect on your learning algorithm. But really, don't turn to Batch norm as a regularization. Use it as a way to normalize your hidden units, activations, and therefore speed up learning. And I think the regularization is an almost unintended side effect. So I hope that gives you better intuition about what Batch norm is doing. Before we wrap up the discussion on Batch norm, there's one more detail I want to make sure you know, which is that Batch norm handles data one mini batch at a time. It computes mean and variances on mini batches. So at test time, you're trying to make predictions, trying to evaluate the neural network. You might not have a mini batch of examples. You might be processing one single example at a time. So at test time, you need to do something slightly differently to make sure your predictions make sense. In the next and final video on Batch norm, let's talk over the details of what you need to do in order to take your neural network trained using Batch norm to make predictions. Batch norm processes your data one mini batch at a time, but at test time, you might need to process the examples one at a time. Let's see how you can adapt your network to do that. Recall that during training, here are the equations you'd use to implement Batch norm. Within a single mini batch, you'd sum over that mini batch of the ZI values to compute the mean. So here, you're just summing over the examples in one mini batch. I'm using M to denote the number of examples in the mini batch, not in the whole training set. Then you compute the variance, and then you compute Z norm by scaling by the mean and standard deviation with epsilon added for numerical stability. And then Z tilde is taking Z norm and rescaling by gamma and beta. So notice that mu and sigma squared, which you need for this scaling calculation, are computed on the entire mini batch. But at test time, you might not have a mini batch of 64, 128, or 256 examples to process at the same time. So you need some different way of coming up with mu and sigma squared. And if you have just one example, taking the mean and variance of that one example doesn't make sense. So what's actually done in order to apply your neural network at test time is to come up with some separate estimate of mu and sigma squared. And in typical implementations of Batch norm, what you do is estimate this using a exponentially weighted average, where the average is across the mini batches. So to be very concrete, here's what I mean. Let's pick some layer L, And let's say you're going through mini batches x1, x2, together with the corresponding values of y, and so on. So when training on x1, for that layer L, you get some mu L. And in fact, I'm going to write this as mu for the first mini batch and that layer. And then when you train on the second mini batch, for that layer and that mini batch, you end up with some second value of mu. And then for the third mini batch, in this hidden layer, you end up with some third value for mu. So just as we saw how to use an exponentially weighted average to compute the mean of theta 1, theta 2, theta 3 when you are trying to compute a exponentially weighted average of the current temperature, you would do that to keep track of sort of what's the latest average value of this mean vector you've seen. So that exponentially weighted average becomes your estimate for what the mean of the z's is for that hidden layer. And similarly, you use an exponentially weighted average to keep track of these values of sigma squared that you see on the first mini batch in that layer, sigma squared that you see on the second mini batch, and so on. So you keep a running average of the mu and the sigma squared that you're seeing for each layer as you train the neural network across different mini batches. Then finally, at test time, what you do is, in place of this equation, you would just compute z norm using whatever value z you have and using your exponentially weighted average of the mu and sigma squared, whatever was the latest value you have, to do the scaling here. And then you would compute z tilde on your one test example using that z norm that we just computed on the left and using the beta and gamma parameters that you had learned during your neural network training process. So the takeaway from this is that during training time, mu and sigma squared are computed on an entire mini batch of, say 64, 128, or some number of examples. But at test time, you might need to process a single example at a time. So the way to do that is to estimate mu and sigma squared from your training set. And there are many ways to do that. You could, in theory, run your whole training set through your final network to get mu and sigma squared. But in practice, what people usually do is implement an exponentially weighted average, where you just keep track of the mu and sigma squared values you're seeing during training, and use an exponentially weighted average, also sometimes called a running average, to just get a rough estimate of mu and sigma squared. And then you use those values of mu and sigma squared at test time to do the scaling you need of the hidden unit values z. In practice, this process is pretty robust to the exact way you use to estimate mu and sigma squared. So I wouldn't worry too much about exactly how you do this. And if you're using a deep learning framework, they'll usually have some default way to estimate the mu and sigma squared that should work reasonably well as well. But in practice, any reasonable way to estimate the mean and variance of your hidden unit values z should work fine at test. So that's it for batch norm, and using it, I think you'll be able to train much deeper networks and get your learning algorithm to run much more quickly. Before we wrap up for this week, I want to share with you some thoughts on deep learning frameworks as well. Let's start to talk about that in the next video. So far, the classification examples we've talked about have used binary classification, where you had two possible labels, 0 or 1. Is it a cat or is it not a cat? What if you have multiple possible classes? There's a generalization of logistic regression called Softmax Regression that lets you make predictions where you're trying to recognize one of C or one of multiple classes rather than just recognize two classes. Let's take a look. Let's say that instead of just recognizing cats, you want to recognize cats, dogs, and baby chicks. So I'm going to call cats class 1, dogs class 2, baby chicks class 3. And if none of the above, then there's an other or a none of the above class, which I'm going to call class 0. So here's an example of the images and the classes they belong to. That's a picture of a baby chick, so the class is 3, cat is class 1, a dog is class 2. That's I guess that's a koala, so that's a none of the above, so that's class 0, class 3, and so on. So the notation we're going to use is, I'm going to use capital C to denote the number of classes you're trying to categorize your inputs into, and in this case, you have 4 possible classes, including the other or the none of the above class. So when you have 4 classes, the numbers indexing your classes would be 0 through C minus 1, through capital C minus 1. So in other words, it would be 0, 1, 2, or 3. In this case, we're going to build a neural network where the outputs layer has 4, or in this case, the variable capital alphabet C output units. So n, the number of units in the output layer, which is layer L, is going to be equal to 4, or more generally, is going to be equal to C. And what we want is for the number of units in the output layer to tell us what is the probability of each of these 4 classes. So the first node here is supposed to output, or we want it to output, the probability that is the other class, given the input x. This will output probability that is a cat, given x. This will output probability that is a dog, given x. That will output the probability. I'm just going to abbreviate baby chick to be BC. So probably have a baby chick abbreviated BC, given the input x. So here, the output labels y hat is going to be a 4 by 1 dimensional vector because it now has to output 4 numbers, giving you these 4 probabilities. And because probabilities should sum to 1, the 4 numbers in the output y hat, they should sum to 1. The standard model for getting a neural network to do this uses what's called a softmax layer in the output layer in order to generate these outputs. Let me write down the map and then we can come back and get some intuition about what the softmax layer is doing. So in the final layer of the neural network, you are going to compute as usual the linear part of the layer. So z capital L, that's the z variable for the final layer. So remember, this is layer capital L. So as usual, you compute that as WL times the activation of the previous layer plus the biases for that final layer. Now, having computed z, you now need to apply what's called the softmax activation function. So the activation function is a bit unusual for the softmax layer, but this is what it does. First, we're going to compute a temporary variable, which I'm going to call t, which is e to the zl. So this is applied element-wise. So zl here, in our example, zl is going to be 4 by 1. It's a 4-dimensional vector. So t itself, e to the zl, that's an element-wise exponentiation. T will also be a 4 by 1 dimensional vector. Then the output, al, is going to be basically the vector t, but normalized to sum to 1. So al is going to be e to the zl divided by sum from j equals 1 through 4, because we have 4 classes of t subscript I. So another way of saying this is that al is also a 4 by 1 vector, and the ith element of this 4-dimensional vector, let's write that al subscript I, this is going to be equal to ti over sum of ti. Okay. In case this math isn't clear, we'll do an example in a minute that'll make this clearer. So in case this math isn't clear, let's go through a specific example that will make this clearer. Let's say that you've computed ZL, and ZL is a 4-dimensional vector. Let's say it's 5, 2, -1, 3. What we're going to do is use this element-wise exponentiation to compute this vector t. So t is going to be e to the 5, e to the 2, e to the -1, e to the 3. And if you plug that into a calculator, these are the values you get. E to the 5 is 148.4, e squared is about 7.4, e to the -1 is 0.4, and e cubed is 20.1. And so the way we go from the vector t to the vector al is to just normalize these entries to sum to 1. So if you sum up the elements of t, if you just add up those 4 numbers, you get 17.4 So finally, AL is just going to be this vector t as a vector divided by 176.3. So for example, this first node here, this will output e to the 5 divided by 176.3, and that turns out to be 0.842. So saying that for this image, if this is the value of z you get, the chance of it being class 0 is 84.2%. And then the next node outputs e squared over 176.3. That turns out to be 0.042. So it's 4.2% chance. The next one is e to negative 1 over that, which is 0.002. And the final one is e cubed over that, which is 0.114. So about an 11.4% chance that this is class number 3, which I guess is the baby chick class, right? So there's a chance of it being class 0, class 1, class 2, class 3. So the output of the neural network, AL, this is also y hat. This is a 4x1 vector where the elements of this 4x1 vector are going to be these 4 numbers that we just computed. So this algorithm takes the vector ZL and maps it to 4 probabilities that sum to 1. And if we summarize what we just did to map from ZL to AL, this whole computation, computing the exponentiation to get this temporary variable t, and then normalizing, we can summarize this into a softmax activation function and say AL equals the activation function g applied to the vector ZL. The unusual thing about this particular activation function is that this activation function g, it takes as input a 4x1 vector and it outputs a 4x1 vector. So previously, our activation functions used to take in a single real value input. So for example, the sigmoid and the value activation functions input a real number and output a real number. The unusual thing about the softmax activation function is because it needs to normalize across the different possible outputs, it needs to take in a vector of inputs and then outputs a vector. So what are the things that a softmax classifier can represent? I'm going to show you some examples where you have inputs x1, x2, and these feed directly to a softmax layer that has 3 or 4 or more output nodes that then outputs y hat. So I'm going to show you a neural network with no hidden layer, and all it does is compute z1 equals w1 times the input x plus b, and then the output a1 or y hat is just the softmax activation function applied to z1. So in this neural network with no hidden layer, it should give you a sense of the types of things a softmax function can represent. So here's one example with just raw inputs x1 and x2, a softmax layer with c equals 3 output classes can represent this type of decision boundary. Notice it's kind of a several linear decision boundaries, but this allows it to separate out the data into 3 classes. And in this diagram, what we did was we actually took the training set that's kind of shown in this figure and trained the softmax classifier with 3 output labels on the data, and then the color on this plot shows thresholding the outputs of the softmax classifier and coloring in the input based on which one of the 3 outputs had the highest probability. So we can maybe kind of see that this is like a generalization of logistic regression with sort of linear decision boundaries, but with more than 2 classes, with instead of the classes being just 0, 1, the classes can be 0, 1, or 2. Here's another example of the decision boundary that a softmax classifier can represent when trained on a dataset with 3 classes. And here's another one, right? So this is, but one intuition is that the decision boundary between any 2 classes will be linear. That's why you see, for example, the decision boundary between the yellow and the red classes, that's sort of a linear boundary. Between the purple and red is not a linear decision boundary. Between the purple and yellow is another linear decision boundary. But, it was able to use these different linear functions in order to separate the space into 3 classes. Let's look at some examples with more classes. So this is an example with c equals 4 so that the green class in softmax can continue to represent these types of linear decision boundaries between multiple classes. So here's one more example with C equals 5 classes, and here's one last example with C equals 6. So this shows the type of things a softmax classifier can do when there is no hidden layer. Of course, you have a much deeper neural network with X, and then, some hidden units, and then more hidden units, and so on. Then you could learn even more complex nonlinear decision boundaries to separate out multiple different classes. So I hope this gives you a sense of what a softmax layer, what a softmax activation function in a neural network can do. In the next video, let's take a look at how you can train a neural network that uses a softmax layer. In the last video, you learned about the softmax layer and the softmax activation function. In this video, you deepen your understanding of softmax classification and also learn how to train a model that uses a softmax layer. Recall our earlier example where the output layer computes ZL as follows. So if you have 4 classes, C equals 4, then ZL is going to be 4 by 1-dimensional vector. And we said we compute T, which is this temporary variable that performs element-wise exponentiation. And then finally, if the activation function for your output layer, G of L, is the softmax activation function, then the output will be this. It's basically taking that temporary variable T and normalizing it to sum to 1. So this then becomes A of L. So you notice that in the Z vector, the biggest element was 5, and the biggest probability ends up being this first probability. The name softmax comes from contrasting it to what's called a hardmax, which would have taken the vector Z and mapped it to this vector. So hardmax function would look at the elements of Z and just put a 1 in the position of the biggest element of Z, and then zeros everywhere else. And so this is a very hardmax, where the biggest element gets a output of 1 and everything else gets an output of 0. Whereas in contrast, the softmax is a more gentle mapping from Z to these probabilities. So I'm not sure if this is a great name, but at least that was the intuition behind why we call it a softmax. Is in contrast to the hardmax. And one thing I didn't really show, but had alluded to, is that Softmax regression, or the softmax activation function, generalizes the logistic activation function to C classes rather than just 2 classes. And it turns out that if C is equal to 2, then softmax with C equals to 2 essentially reduces to logistic regression. And I'm not going to prove this in this video, but the rough outline for the proof is that if C equals to 2 and if you apply softmax, then the output layer, AL, will output 2 numbers if C equals 2. So maybe it outputs 0.842 and 0.158, right? And these 2 numbers always have to sum to 1. And because these 2 numbers always have to sum to 1, they're actually redundant. And maybe you don't need to bother to compute 2 of them. Maybe you just need to compute 1 of them. And it turns out that the way you end up computing that number reduces to the way that logistic regression is computing its single output. So that wasn't much of a proof, but the takeaway from this is that softmax regression is a generalization of logistic regression to more than 2 classes. Now let's look at how you would actually train a neural network with a softmax output layer. So in particular, let's define the loss function you use to train your neural network. Let's take an example. Let's say you have an example in your training set where the output is where the target output, the ground truth label, is 0100. So the example from the previous video, this means that this is an image of a cat because it falls into class 1. And now let's say that your neural network is currently outputting y hat equals, so y hat would be a vector of probabilities, got to sum to 1, 0.1, 0.4. So you can check that sums to 1, and this is going to be a L. So the neural network is not doing very well in this example because this is actually a cat and assigned only a 20% chance that this is a cat. So it didn't do very well in this example. So what's the loss function you would want to use to train this neural network? In softmax classification, the loss we typically use is negative sum of j equals 1 through 4, and it's really sum from 1 to c in the general case. I'll just use 4 here, of y log yj log y hat of j. So let's look at our single example above to better understand what happens. Notice that in this example, y1 equals y3 equals y4 equals 0, because those are zeros and only y2 is equal to 1. So if you look at this summation, all the terms with 0 values of yj will equal to 0, and the only term you're left with is negative y2 log y hat 2, because when you sum over the indices of j, all the terms will end up 0 except when j is equal to 2. And because y2 is equal to 1, this is just negative log y hat 2. So what this means is that if your learning algorithm is trying to make this small, because you use gradient descent to try to reduce the loss on your training set, then the only way to make this small is to make this small, and the only way to do that is to make y hat 2 as big as possible. And these are probabilities, so it can never be bigger than 1, but this kind of makes sense, because if x for this example is a picture of a cat, then you want that output probability to be as big as possible. So more generally, what this loss function does is it looks at whatever is the ground truth class in your training set, and it tries to make the corresponding probability of that class as high as possible. If you're familiar with maximum likelihood estimation in statistics, this turns out to be a form of maximum likelihood estimation. But if you don't know what that means, don't worry about it. The intuition we just talked about will suffice. Now, this is the loss on a single training example. How about the cost, j, on the entire training set? So the cost of setting the parameters, and so on, of all the weights and biases, you define that as pretty much what you guess, sum over your entire training set of the loss, your learning algorithm's predictions, summed over your training examples. And so what you do is use gradient descent in order to try to minimize this cost function. Finally, one more implementational detail. Notice that because c is equal to 4, y is a 4 by 1 vector, and y hat is also a 4 by 1 vector. So if you're using a vectorized implementation, the matrix capital Y is going to be y1, y2 through ym, stacked horizontally. And so, for example, if this example up here is your first training example, then the first column of this matrix Y will be 0, 1, 0, 0, and then your second example, maybe the second example is a dog, maybe the third example is a none of the above, and so on. And then this matrix capital Y will end up being a 4 by m dimensional matrix. And similarly, y hat will be y hat 1 stacked up horizontally going through y hat m. So if this is actually y hat 1, or the output on the first training example, then y hat will be this 0.3, 0.2, 0.1, 0.4, and so on. And y hat itself will also be a 4 by m dimensional matrix. Finally, let's take a look at how you'd implement gradient descent when you have a softmax output layer. So this output layer will compute ZL, which is C by 1 in our example, 4 by 1, and then you apply the softmax activation function to get AL, or y hat, and then that in turn allows you to compute the loss. So we've talked about how to implement the forward propagation step of the neural network to get this output and to compute that loss. How about the back propagation step, or gradient descent? Turns out that the key step, or the key equation you need to initialize backprop is this expression that the derivative with respect to z at the last layer, this turns out you can compute as y hat, the 4 by 1 vector, minus y, the 4 by 1 vector. So you notice that all of these are going to be 4 by 1 vectors when you have 4 classes, and c by 1 in the more general case. And so this, going by our usual definition of what is dz, this is a partial derivative of the cost function with respect to zl. If you're an expert in calculus, you can derive this yourself. Or if you're an expert in calculus, you can try to derive this yourself, but using this formula will also just work fine if you ever need to implement this from scratch. But with this, you can then compute dzl and then sort of start off the backprop process to compute all the derivatives you need throughout your neural network. But it turns out that in this week's programming exercise, we'll start to use one of the deep learning programming frameworks. And for those programming frameworks, usually it turns out you just need to focus on getting the forward prop right. And so long as you specify the programming framework, the forward prop pass, the programming framework will figure out how to do back prop, or how to do the backward pass for you. So this expression is worth keeping in mind for if you ever need to implement softmax regression or softmax classification from scratch, although you won't actually need this in this week's programming exercise because the programming framework you use will take care of this derivative computation for you. So that's it for softmax classification. With it, you can now implement learning algorithms to categorize your inputs into not just one of two classes, but one of C different classes. Next, I want to show you some of the deep learning programming frameworks which can make you much more efficient in terms of implementing deep learning algorithms. Let's go on to the next video to discuss that. You've learned to implement deep learning algorithms more or less from scratch using Python and NumPy. And I'm glad you did that because I wanted you to understand what these deep learning algorithms are really doing. But you find that as you implement more complex models, such as convolutional neural nets or recurrent neural networks, or as you start to implement very large models, that is increasingly not practical, at least for most people, is not practical to implement everything yourself from scratch. Fortunately, there are now many good deep learning software frameworks that can help you implement these models. To make an analogy, I think that hopefully you understand how to do a matrix multiplication, and you should be able to implement, how to code to multiply two matrices yourself. But as you build very large applications, you probably not want to implement your own matrix multiplication function, but instead you want to call a numerical linear algebra library that could do it more efficiently for you. But it still helps that you understand how multiplying two matrices work. So I think deep learning has now matured to that point where it's actually more practical and you'll be more efficient doing some things with some of the deep learning frameworks. So let's take a look at the frameworks out there. Today, there are many deep learning frameworks that makes it easy for you to implement neural networks, and here are some of the leading ones. Each of these frameworks has a dedicated user and developer community, and I think each of these frameworks is a credible choice for some subset of applications. There are a lot of people writing articles comparing these deep learning frameworks and how well these deep learning frameworks changes. And because these frameworks are often evolving and getting better month to month, I'll leave you to do a few internet searches yourself if you want to see the arguments on the pros and cons of some of these frameworks. But I think many of these frameworks are evolving and getting better very rapidly. So rather than too strongly endorsing any of these frameworks, I want to share with you the criteria I would recommend you use to choose frameworks. One important criteria is the ease of programming, and that means both developing the neural network and iterating on it, as well as deploying it for production, for actual use by thousands or millions or maybe hundreds of millions of users, depending on what you're trying to do. A second important criteria is running speeds. Especially if you're training on large data sets, some frameworks will let you run and train your neural network more efficiently than others. And then one criteria that people don't often talk about, but I think is important, is whether or not the framework is truly open. And for a framework to be truly open, it needs not only to be open source, but I think it needs good governance as well. Unfortunately, in the software industry, some companies have a history of open sourcing software, but maintaining single corporation control of the software. And then over some number of years, as people start to use their software, some companies have a history of gradually closing off what was open source, or perhaps moving functionality into their own proprietary cloud services. So one thing I pay a bit of attention to is how much you trust that a framework will remain open source, for a long time, rather than just being under the control of a single company, which for whatever reason may choose to close it off in the future, even if the software is currently released under open source. But at least in the short term, depending on your preferences of language, whether you prefer Python or Java or C++ or something else, and depending on what application you're working on, whether it's computer vision or natural language processing or online advertising or something else, I think multiple of these frameworks could be a good choice. So that's it on programming frameworks. By providing a higher level of abstraction than just a numerical linear algebra library, any of these programming frameworks can make you more efficient as you develop machine learning applications. Hi, and welcome back. There are a few deep learning programming frameworks that can help you be much more efficient in how you develop and use deep learning algorithms. One of these frameworks is TensorFlow. What I hope to do in this video is step through with you the basic structure of a TensorFlow program so that you know how you could use TensorFlow to implement such programs, implement neural networks yourself. And then after this video, I'll leave you to dive into some more of the details and gain practice programming with TensorFlow in this week's programming exercise. This week's programming exercise does require a little extra time, so please do plan or budget for a little bit more time to complete it. As a motivating problem, let's say that you have some cost function j that you want to minimize. And for this example, I'm going to use this highly simple cost function j of w equals w squared minus 10w plus 25. So that's the cost function. You might notice that this function is actually w minus 5 squared. If you expand out this quadratic, you get the expression above. And so the value of w that minimizes this is w equals 5. But let's say we didn't know that, and you just have this function. Let's see how you can implement something in TensorFlow to minimize this. Because a very similar structure of program can be used to train neural networks, where you can have some complicated cost function j of wb depending on all the parameters of your neural network. And then similarly, you'll be able to use TensorFlow to automatically try to find values of w and b that minimize this cost function. But let's start with the simpler example on the left. So here I am in Python in my Jupyter notebook. In order to start up TensorFlow, you type import numpy or numpy as np, import TensorFlow as tf. So this is idiomatic. This is what pretty much everyone types exactly to import TensorFlow as tf. Next thing you want to do is define the parameter w. In TensorFlow, you're going to use tf.variable to signify that this is a variable, initialize it to 0, and the type of the variable is a floating point number. So dtype equals tf.float32. So it's a TensorFlow floating point number. Next, let's define the optimization algorithm we're going to use. In this case, the Adam optimization algorithm. So optimizer equals tf.keras.optimizers.adam. And let's set the learning rate to 0.1. Now we can define the cost function. Remember, the cost function was w squared minus 10w plus 25. So let me write that down. The cost is w squared minus 10w plus 25. The great thing about TensorFlow is you only have to implement forward prop. That is, you only have to write the code to compute the value of the cost function, and TensorFlow can figure out how to do the back prop or do the gradient computation. One way to do this is to use gradient tape. Let me show you the syntax. With tf.gradient tape as tape, compute the cost as follows. The intuition behind the name gradient tape is by an analogy to the old school cassette tapes, where gradient tape will record the sequence of operations as you're computing the cost function in the forward prop step. And then when you play the tape backwards, in backwards order, it can revisit the order of operations in reverse order, and along the way, compute backprop and the gradients. Now, let's define a training step function to loop over. We're going to define a single training step as this function. In order to carry out one iteration of training, you have to define what are the trainable variables. So trainable variables is just a list with only W. And we're then going to compute the gradients with this, with the tape, cost trainable variables. Having done this, you can now use the optimizer to apply the gradients, and the gradients are grads and trainable variables. And the syntax we're going to use is we're actually going to use the zip function, it's a built-in Python function, to take the list of gradients, take the list of trainable variables, and pair them up. So that the gradients and the zip function just takes these two lists and pairs up the corresponding elements. I'm going to type print W here just to print the initial value of W. We've not actually run train step yet. So, all right, hopefully I have no syntax errors. So W is initially the value of 0, which is what we have initialized it to. And now let's run one step of our little learning algorithm and print the new value of W. And now it's increased a little bit from 0 to about 0.1. Now let's run 1,000 iterations of our train step. So for I in range, 1,000 train step, print W, and let's see what happens. Run pretty quickly. And now W is nearly 5, which we knew was the minimum of this cost function. So isn't that cool? We just specified the cost function, didn't have to take derivatives, and TensorFlow figured out how to minimize this for us. I hope this gives you a sense of the broad structure of a TensorFlow program. And as you do this week's programming exercise and play more with TensorFlow code yourself, some of these functions that I just used here will become more familiar. Just a couple things to notice. W is the parameter you want to optimize. So that's why we declared W as a variable. And all we had to do was use a gradient tape to record the order of the sequence of operations needed to compute the cost function. And that was forward prop. And TensorFlow could figure out automatically how to take derivatives with respect to the cost function. And that's why in TensorFlow, you basically have to only implement the forward prop step, and it will figure out how to do the gradient computation. Now, there's one more feature of TensorFlow that I want to show you. In the example we went through so far, the cost function is a fixed function of the parameter or the variable W. But what if the function you want to minimize is a function of not just the parameters, of not just W, but also a function of your training set? So let's say you have some training data X and X or Y, and you're training a neural network where the cost function depends on your data X or X and Y, as well as the parameters W. How do you get that training data into a TensorFlow program? Let's go through another version of how to implement all this. I'm still going to define W as the variable. Also going to use the Adam optimizer, but now I'm going to define X as a list of numbers, as an array, and I'm going to plug in 1, -10, and 25, and this will be another float 32. So these three numbers, 1, -10, and 25, will play the role of the coefficients of the cost function. So you can think of X as being like data that controls the coefficients of this quadratic cost function. So let me now define the cost function, which we're going to minimize as same as before, except that now I'm going to write X of 0 times that plus X of 1 times that, this plus X2. So this is the same cost function as the one above, except that the coefficients are now controlled by this, little piece of data X that we have. So now this cost function computes exactly the same cost function as you had above, except that this little piece of data in the array X controls the coefficients of the quadratic cost function. Now, let me write print W. This should do nothing because W, is still 0. It's just the initial value. But if you then use the optimizer to take one step of the optimization algorithm, then let's print W again. Let's see if that works. Great. Now this has taken one step of Adam optimization, and so W is again roughly 0.1. So the syntax optimizer.minimize cost function and then list of variables W, that is a simpler alternative piece of syntax, or does the same thing as these lines up above with the gradient tape and apply gradients. Now that we have a single training step implemented, let's put the whole thing in a loop. Def training X W optimizer, define the cost function within the scope of this function, and then for I in range 1000, let's run 1000 iterations, and then we will return W. So let's see what that does. There you go. And now W is nearly at the minimum, set to roughly the value of 5. So hopefully this gives you a sense of what TensorFlow can do. And the thing that makes it so powerful is all you need to do is specify how to compute the cost function. And then it takes derivatives and it can apply an optimizer with pretty much just 1 or 2 lines of code. So here's the code again. And in case some of these functions or variables still seem a little bit mysterious to you, they will become more familiar after you've practiced with it a couple times by working through the programming exercise. So what is this code really doing? Let's focus on this equation. The heart of a TensorFlow program is something to compute the cost, and then TensorFlow automatically figures out the derivatives and how to minimize the cost. So what this line of code is doing is allowing TensorFlow to construct a computation graph. And what a computation graph does is the following. It takes x0 and it takes w, and w gets squared, so that's w squared. And then x0 and w squared get multiplied together to give x0 times w squared, and so on through multiple steps until eventually this gets built up to compute the cost function. I guess the last step would have been adding in that last coefficient, x2. The nice thing about TensorFlow is that by implementing basically forward prop through this computation graph, TensorFlow will automatically figure out all the necessary backward calculations. And it will automatically be able to figure out all the necessary backward steps needed to implement backprop. Isn't that nice? And that's why you don't need to explicitly implement backprop. TensorFlow figures it out for you. And this is one of the things that makes the programming frameworks help you become really efficient. And there are also a lot of things you can change with just one line of code. For example, if you don't want to use the Adam optimizer and you want to use a different one, then just change this one line of code. And you can quickly swap it out for a different optimization algorithm. All of the popular modern deep learning programming frameworks support things like these, and it makes it much easier to develop even pretty complex neural networks. So I hope that gave you a sense of the typical structure of a TensorFlow program. To recap material from this week, you saw how to systematically organize the hyperparameter search process. You also saw batch normalization and how you can use that to speed up your neural network training. And we also chatted about deep learning programming frameworks, and you learned about TensorFlow. I hope that you go on and try out and enjoy this week's programming exercise, which will help you to gain even greater familiarity with these ideas.